Hello there, and welcome to Science for Sleep, a place where the biggest ideas in the universe settle down and move at the same pace as your breath, slow enough to follow without strain, and gentle enough to meet you exactly where you are. Tonight we're going to wander toward one of the strangest limits nature has ever placed on itself, a boundary so extreme that even our most advanced theories falter when they try to describe it. It's called the Planck energy. You can think of it as the maximum amount of energy the universe seems willing to allow in a single interaction, before everything we understand begins to reshape into something unfamiliar. Nothing about it requires urgency. There is no rush to reach the edge of comprehension. We're simply drifting there together, letting curiosity set the rhythm. Before we go any farther, I'd love to know something small about you. Something simple enough to settle a mind before we lift our attention to anything cosmic. Where are you listening from tonight, and what time does your clock show right now? Maybe it's evening where you are and the day has softened a little. Maybe it's early morning and you're easing into wakefulness. Or maybe it's somewhere in between, a quiet in-between hour when the world feels paused. Whatever the moment, I'm glad you're here, and I hope this journey becomes a calm space for you. Even as the ideas themselves stretch far beyond everyday experience. If you find these slow explorations soothing or helpful for winding down, I'd be grateful if you'd consider giving the video a like or subscribing. It helps this little corner reach others who might also be searching for something gentle to learn from as they rest. And if this exploration happens to drift you towards sleep, that's perfectly all right. The universe will still be here when you wake, and these questions about its deepest limits will still be waiting like quiet companions you can return to at any time. To begin, imagine holding a scale in your mind, not one with numbers you'd see in a classroom, but simply the idea of measuring things: energy, length, time, mass, all the basic quantities physics relies on to describe how nature behaves. Most of the time, these quantities feel manageable. We know what a meter is, we know what a second is. We have some sense of what a joule of energy means, even if it's faint. But every field eventually runs into a point where the tools that usually work begin to fall short. The Planck scale is one of those points. It sits so far beyond anything we can reach in practice that it becomes more of a conceptual boundary than a practical target. This is the place where the numbers become so large or so small that they stop behaving like anything we can anchor to experience. When physicists talk about the Planck energy, they're referring to the amount of energy you would need to probe distances so tiny that even the structure of spacetime itself stops being smooth. At ordinary scales, even incredibly small ones, spacetime behaves like a consistent fabric. You can picture it as something stable enough to measure distances and define directions. But at the Planck scale, that fabric is expected to become agitated in a way we don't yet know how to describe. Tiny fluctuations appear. The spacing between points seems to shift unpredictably. The reliable geometry of the universe begins to behave more like a restless sea, where no two moments look exactly the same. This is one of the reasons the Planck energy is often described as the threshold where our current laws of physics lose their clarity. To understand why this happens, it helps to think about the two pillars of modern physics that usually serve us quite well. One is quantum mechanics, the theory that handles the behavior of particles and the way probabilities govern their motion. The other is general relativity, which describes gravity and the curvature of space-time. Both theories are incredibly successful in their own domains. Quantum mechanics handles the smallest scales. General relativity handles the largest, but they don't merge smoothly when you try to apply both at once. For most conditions in the universe, we can get away with treating them separately, but the Planck energy is not most conditions. It represents the point where quantum fluctuations grow so intense that they influence space-time itself, something only general relativity is meant to describe. When these two theories try to operate simultaneously at full strength, they produce contradictions. This breakdown tells us that the Planck energy is not just another large number, but a fundamental limit built into the structure of nature. Of course, reaching this energy in any laboratory is impossible. With our current understanding of technology, not just for practical reasons, but for conceptual ones. Even the most powerful particle accelerators humanity has constructed fall short by an extraordinary margin. To compare them is almost to stretch the meaning of comparison. A single collision at the Planck energy would require conditions far beyond anything a human-made device could sustain. It would be like trying to lift a mountain with a feather. The gap is not one we can bridge with incremental improvements. It's a gulf that suggests we may never reach those energies directly, relying instead on indirect clues or theoretical reasoning. Yet even though the Planck scale is inaccessible, it still carries profound importance. Physicists treat it as the point where a deeper, unified theory of nature must reveal itself. A theory that seamlessly weaves together the rules governing tiny particles and the rules shaping cosmic structures. The Planck energy is not only a boundary, but also a signpost pointing toward whatever comes next in our understanding. It tells us where the known rules begin to bend, where the assumptions we rely on no longer hold, and where new ideas must take their place. It guides inquiry, even if it can't be tested directly. And in many ways, it reminds us that the universe has layers still hidden from view. All of this sets the stage for the path we're wandering tonight, one that doesn't aim to force clarity where clarity doesn't exist, but simply to look calmly at how physicists approach these extremes. Instead of treating the Planck energy as an unreachable summit, we can treat it as a distant landscape, something we survey from afar, examining the hints, the reasoning, and the consequences that emerge as we approach it conceptually. There is no need to rush through the details. Each step reveals something about how the universe organizes itself at the deepest levels. Moving slowly from the threshold we set a moment ago, the conversation turns toward a place in physics where the usual confidence of equations softens, not because the ideas lose importance, but because the universe becomes less cooperative the closer we move toward its deepest foundations. There are regions in science where the rules feel firm, where a formula tells you everything you need to know with crisp precision. Then there are regions where the rules still work but must be held delicately, with a kind of awareness that they may not behave as expected if pushed too far. And finally, there is the region near the Planck scale, where the rules begin to blur, not in a dramatic or chaotic way, but in a way that feels like listening to a voice that grows quieter as you approach it. That quietness doesn't imply uncertainty in the everyday sense. It's the universe signaling that the framework used to describe it is nearing its limit. In most areas of physics, you can ask a question and expect an answer that follows naturally from established laws. If you want to know how fast an object falls, you use gravity. If you want to know how an electron behaves in an atom, quantum mechanics provides the tools. If you want to know how planets orbit a star, general relativity guides the calculation. These are places where physics speaks clearly, offering models tested again and again with remarkable reliability. But as you nudge those questions into extreme conditions where energy densities rise far beyond what nature normally allows, the clarity begins to fade. Patterns we usually treat as stable begin to lose their shape. Concepts that once felt sharply defined become slippery. This isn't because scientists have overlooked something simple, it's because the structure of nature itself demands a different language once energy reaches a certain intensity. To understand what that whispering means, it helps to think about the assumptions embedded in most physical theories. Every equation rests on conditions that must hold for it to be valid. A familiar example is the way Newtonian mechanics works perfectly well for everyday speeds, but breaks down as you approach the speed of light. Similarly, classical descriptions of matter fail when you shrink to atomic scales, requiring quantum rules instead. So much of physics is built on understanding where one model succeeds and where it gives way to another. The Planck scale is where two of the most successful models we have begin to give way simultaneously. Quantum mechanics and general relativity each work beautifully, but neither survives intact when both must be applied with equal intensity. Imagine describing the behavior of a particle using quantum rules. You treat its position and momentum as probabilistic, and you calculate how its wave function changes over time. Everything fits within a framework that handles uncertainty by design. Now imagine describing the curvature of spacetime using general relativity. You treat mass and energy as sources that shape the geometry around them, and objects move according to that geometry. This too is a reliable and elegant approach. But now imagine a situation where a particle is compressed into a region so tiny that its quantum fluctuations create enormous concentrations of energy. That energy then forces spacetime to curve violently. But in quantum mechanics, spacetime is assumed to be perfectly smooth and rigid, an unmoving background. In general relativity, the motion of particles is assumed to be continuous and classical, not probabilistic or fluctuating. Each theory treats the assumptions of the other as incompatible. This incompatibility becomes overwhelming at the Planck energy. When a particle reaches energies near that scale, the energy is so concentrated that the gravitational effects predicted by relativity become non-negligible. Tiny fluctuations in position create dramatic curvature. Minuscule shifts in momentum distort the geometry. Probabilities and spacetime begin influencing each other in ways that neither theory is equipped to handle. It's like trying to describe the same event using two languages that were never designed to share vocabulary. At ordinary scales, you can translate between them with a bit of care. But at the Planck scale, they stop translating altogether. The difficulty isn't due to a lack of effort. Physicists have spent decades trying to combine the laws that govern the very small with those that shape the very large. String theory, loop quantum gravity, causal sets, and other approaches all attempt to find a way to describe reality when it's compressed into its most extreme form. But none has yet achieved the kind of experimental confirmation that would allow us to treat it as a definitive framework. This is partly because reaching these energies is impossible with current technology, but it's also because the mathematical structures themselves resist easy reconciliation. They hint at deeper rules but do not yet present them in a form everyone agrees on. At more familiar scales, the clarity of physics can feel almost comforting. You can picture the stable orbit of Earth around the Sun, or the predictable path of light bending near a massive object. In those contexts, relativity is dependable. You can picture electrons forming chemical bonds, photons being absorbed or emitted by atoms, and particles moving through a field of probabilities. In those contexts, quantum mechanics is dependable. But near the Planck energy, predictability begins to thin out. The two theories begin speaking at cross purposes, and the clarity they usually offer fades into something uncertain. It's not the uncertainty of randomness, but rather the uncertainty of incomplete description. We know something should happen, we know something does happen, but we do not yet have the right tools to describe it fully. This shift in clarity isn't abrupt. Physics doesn't suddenly break. Instead, the predictions become less reliable as energies climb to unimaginable heights. Small corrections appear first, then those corrections grow, then they begin to interact in ways that stray farther from any known pattern. Finally, they grow so large that the theories producing them no longer make coherent sense. That's the whispering. It's the moment when the universe is no longer revealing its behavior through the rules we've relied on, but instead hinting at rules we haven't yet uncovered. This threshold is especially striking because of how successful our existing theories are in every other context. Relativity can describe black holes and gravitational waves with extraordinary precision. Quantum mechanics can describe the behavior of particles in accelerators, semiconductors, and biological molecules. Neither theory feels incomplete when used in its proper domain, but the Planck scale is where those domains overlap so intensely that neither retains its usual authority. It's like two powerful maps that each describe different parts of a continent and work flawlessly until you reach the region where those parts meet, and suddenly the lines no longer align. The maps weren't drawn incorrectly. They were drawn for different terrains. Approaching this boundary conceptually requires slowing down the assumptions that normally guide us. For example, when we speak about energy at everyday scales, we treat it as something that follows predictable rules of conservation and transfer. But at the Planck energy, the concentration becomes so extreme that our usual intuition about locality, causality, and even dimensionality begins to lose traction. The lengths involved are smaller than any distance we can measure, so small that treating space as continuous becomes questionable. Meanwhile, the time intervals involved are shorter than anything we can observe, so brief that treating time as flowing uniformly becomes equally uncertain. These aren't philosophical concerns, they're mathematical ones. The equations stop behaving in stable ways when you push them too far. One of the most useful ways to think about this boundary is to consider how scientists test the limits of their theories. In many branches of physics, pushing beyond a theory's comfort zone reveals the next layer of understanding. Classical mechanics breaks down at high speeds and relativity takes over. Classical electromagnetism breaks down at atomic scales, and quantum mechanics takes over. But at the Planck scale, there is no widely accepted successor yet. Instead, physicists know that something must take over, but the form that successor takes remains uncertain. The whispering is the sign that we've reached the edge of our conceptual map. You might wonder why this boundary exists at all. Why should the universe impose a maximum meaningful energy, or a minimum meaningful length or time? It's partly because of how measurement itself works. To probe smaller regions of space, you need higher energy. But as that energy increases, the gravitational influence of that energy grows. Eventually, the energy you concentrate into a tiny region becomes so dense that it would create a microscopic black hole. That black hole would prevent you from probing anything smaller, because its own event horizon would block access to the space you were trying to examine. This means that the Planck length isn't just small, it's the smallest region in which measurement can have meaning. Beyond that, your tools break themselves in the process of measuring. This interplay between quantum mechanics and gravity is what turns the Planck scale into a natural limit. Neither theory breaks because of a flaw. They break because measurement reaches a point where the act of observing fundamentally alters the structure of space-time. The whispering isn't a weakness. It's a sign that we've reached a region where the universe behaves differently, a region that requires a description not yet fully formed. The Planck scale may be inaccessible in practice, but it remains one of the most important landmarks in all of physics, not because we can reach it, but because it shows where the known world fades into something still waiting to be understood. As we drift farther into this landscape of extreme energy, the focus turns from the gentle fading of clarity to the actual point where the mathematics we usually trust begins to lose its balance. This is not a sudden collapse or a catastrophic failure, but a gradual shift where the equations start responding differently as the quantities inside them grow beyond the conditions they were built to describe. It's a bit like pushing a familiar tool past its design limits. At first, everything works as expected. Then small inconsistencies appear. Before long, those inconsistencies amplify until the calculations stop making practical sense. In physics, that threshold appears near the Planck scale, especially at the Planck energy, where the numbers involved push the theories into regions where they were never meant to operate without modification. To understand why this happens, it helps to notice how much confidence physics usually has in its equations. Most of the time, even when dealing with extreme environments such as the interior of a star or the collisions inside a particle accelerator, the formulas behave predictably. Quantum mechanics tells you how particles interact. Quantum field theory describes how forces operate through fields that fluctuate and exchange quanta. General relativity tells you how space-time bends under mass and energy. These three pillars are built on assumptions that hold remarkably well across an enormous range of situations, but those assumptions have boundaries hidden inside them, and as we travel toward the Planck energy, the boundaries become visible. Consider the way quantum field theory handles interactions. Every particle is modelled as an excitation in a field, and the strength of those interactions is calculated using perturbation theory, essentially a method that treats the interaction are small enough that each correction to the calculation is manageable. This approach works because the energy exchanged in typical particle experiments is tiny compared to the energy at which the field's own structure would become unstable. Each correction is smaller than the one before it, and the series converges nicely toward an accurate result. But as the energy rises, the corrections grow larger. At some point, they no longer shrink with each step. Instead, they grow so quickly that the mathematical series no longer converges. It becomes impossible to extract a stable value from it. This is one of the signs that the equation is trembling. It is not delivering nonsense, but it is telling us that its underlying assumptions no longer apply. A similar issue arises in general relativity. The theory describes space-time as a smooth continuum, something that can be bent, stretched, or curved without tearing. The equations are differential equations, meaning they rely on the idea that space-time can be divided into infinitely small pieces that still behave like space-time. This works beautifully for planets, stars, galaxies, and black holes. It even works well at atomic scales, because the curvature introduced by such small amounts of mass or energy is negligible. But near the Planck energy, the fluctuations of quantum fields become so large that they create severe disturbances in space-time structure. The assumption that space-time remains smooth at arbitrarily small scales stops being reliable. The equations of relativity assume continuity, but the energy fluctuations demand something more granular. As those fluctuations intensify, the geometry predicted by relativity no longer resembles a smooth surface. It becomes something unpredictable, full of abrupt distortions the theory cannot manage. When the foundations of two major theories start trembling at the same time, the effect becomes more than the sum of its parts. Quantum field theory demands a smooth space-time background to operate. Its equations rely on the idea that fields live on a stable stage. General relativity, however, predicts that the quantum fluctuations at the Planck energy create violent distortions in that very stage. Meanwhile, relativity itself demands classical continuity, but quantum mechanics predicts uncertainty everywhere, including in the fabric its equations rely upon. Both theories lose their footing because each depends on conditions that the other disrupts. The trembling of the equations is not randomness. It's the sign of two incompatible assumptions clashing at the same moment. To illustrate the tension, imagine trying to measure the position of a particle by giving it energy. The more you want to pinpoint its location, the shorter the wavelength of the particle you need, which means higher energy. This follows from basic quantum principles. But once that energy becomes large enough, relativity predicts that the region around the particle collapses into a microscopic black hole. Instead of revealing the particle's position with greater detail, the extreme energy prevents any measurement at all. The black hole's event horizon blocks the information. The two theories, each acting correctly within their domains, produce a contradiction when combined. From the perspective of quantum mechanics, more energy means more precision. From the perspective of relativity, more energy means more gravitational collapse. The two trends collide at the Planck scale, and the equations begin signaling that both cannot be applied simultaneously in the form we currently use. This tension shows up in calculations involving curvature as well. In relativity, curvature is proportional to energy density. In quantum mechanics, reducing the volume in which a particle exists increases its energy uncertainty. As you compress a system into a smaller region, the curvature increases in a way that grows rapidly. Eventually, the curvature becomes so intense that the space-time description breaks down. The equations predict singular behavior, values that grow without limit. These infinities are not physical. They are mathematical indicators that the theory is being pushed past its own structural limits. When infinities appear in physics, they almost always mean the theory needs to be reformulated. Near the Planck energy, infinities appear in abundance. Quantum field theory also encounters these kinds of divergences. As energy increases, the probability amplitudes for certain interactions start to approach unphysical values. Renormalization, The technique used to manage infinities by absorbing them into redefined quantities begins to fail because the infinities become too severe. Renormalization is one of the triumphs of modern physics. It allows theories to give sensible predictions even when intermediate steps include divergent terms. But at the Planck scale, the divergences grow so large that the renormalization procedures no longer tame them. They spiral out of control. Once again, the trembling of the equations is a sign that the theory is being stretched too thin. One of the clearest examples of this instability appears when physicists attempt to quantize gravity. The straightforward approach is to treat gravity like any other force and apply quantum field theory to it. But when this is attempted, the mathematical structures explode with divergences that cannot be renormalized. The theory predicts infinite quantities at every order, and no standard method exists to cancel them out. This suggests that gravity cannot be quantized in the same way as the other forces. Its behavior at small scales is fundamentally different. The trembling becomes unmistakable here. Quantum mechanics tries to impose uncertainty on space-time. Relativity tries to keep space-time continuous. The two demands clash, and the equations reflect that clash through their instability. As the numbers grow larger, another problem emerges. Physical quantities that were once separate begin to merge conceptually. For example, mass, energy, and curvature become intertwined so tightly that it becomes difficult to treat them as distinct entities. At everyday scales, energy influences curvature, but the influence is small enough to be treated separately. Near the Planck energy, however, even slight changes in energy create massive changes in curvature. The relationships that normally stay balanced begin amplifying each other. This feedback loop destabilizes the calculations. The inability to separate concepts that were once treated independently is another sign that the theories are reaching their limits. There's also the question of measurement. Many equations in quantum mechanics assume that time flows uniformly, and that measurements can be made at arbitrarily precise intervals. But near the Planck scale, the concept of a continuous timeline starts to lose meaning. The uncertainty in energy becomes so large that it implies an uncertainty in time through the energy-time uncertainty relation. Meanwhile, relativity ties time to space-time curvature. When curvature becomes unpredictable due to quantum fluctuations, the rate at which time flows becomes uncertain as well. The equations that normally describe time evolution acquire terms that oscillate wildly, refusing to settle into stable solutions. This trembling is not just a mathematical detail, it's a clue that time itself behaves differently at extreme energies. All of these signs point toward a deeper conclusion. The trembling of our equations is evidence that space-time itself may not be fundamental. It may be something that emerges from a deeper structure, something that does not obey the assumptions of continuity that relativity uses, or the assumptions of smooth backgrounds that quantum mechanics relies upon. When physicists say the equations tremble, they are acknowledging that the framework we use is nearing the point where the underlying reality must be described by something else. That something else, however, remains unknown. Despite the difficulty, the trembling is useful. It helps physicists identify which parts of the theories are dependable and which parts must be replaced or extended. It provides a sense of direction, pointing toward regions where new physics must appear. The instability is not a failure but a guide. It highlights the assumptions that break down and the questions that must be asked next. And even though it prevents exact calculations at these energies, it makes clear that the Planck scale is not an arbitrary limit. It is a natural one built into the structure of the equations themselves. As we continue easing deeper into the terrain where familiar concepts begin shrinking into something almost unrecognizable, the mind naturally tries to picture what it means for the universe to hold a scale so small that even atoms, which already feel impossibly tiny, start to look enormous by comparison. The human sense of size doesn't stand much of a chance here. Our intuition is built from objects we can touch, places we can stand in, and distances we can walk. Even when we shrink those impressions down to microscopic levels like cells or molecules, we still retain the idea that things occupy a space that can be imagined. But the scale associated with the Planck length, and therefore the Planck energy, sits so far beyond what imagination usually handles that even the smallest known structures take on a kind of monumental quality beside it. At this level, the atom, the nucleus, and the fundamental particles all appear more like vast landscapes than tiny points. To begin to appreciate this contrast, it helps to step slowly through the sizes we do understand. The atoms that make up everything around us are themselves mostly empty space, with a nucleus at the centre and electrons arranged in a cloud around it. Even though the atom is already incredibly small, around 1/10 of a billionth of a metre across, it still contains structure. You can imagine it the way you might imagine a solar system scaled down to an almost incomprehensible degree. The nucleus, sitting at the centre, is much smaller still, roughly 100,000 times smaller than the atom as a whole. Inside that nucleus are protons and neutrons, each only 1/trillionth of a centimetre in size, and those particles themselves are made of quarks held together by gluons. As you descend through these layers, the scale shrinks quickly, but not yet dramatically enough to reach the kind of smallness we are approaching. Even the elementary particles that form the nuclei do not come anywhere near the Planck length. The distances associated with their interactions might suggest something tiny, but compared with the Planck scale, they tower like mountains. If you picture a proton as a region of space filled with swirling energy fields, constantly exchanging quarks and gluons, you might think there is nothing smaller to descend into. Yet the proton is roughly 20 orders of magnitude larger than the Planck length. That is a difference so vast that it almost flips the relationship between small and large. The gap between proton size and the Planck length is greater than the gap between the proton and an object the size of a star. When physicists say the Planck length makes atoms look huge, this is what they mean. To put this into more familiar terms, you might imagine shrinking an atom down to the size of a single grain of sand. The Planck length, on that same scale, would be smaller than a single atom compared with the size of Earth. Even that comparison does not fully capture the extremeness of it, because the lengths involved span so many orders of magnitude that ordinary analogies start to lose effectiveness. It is not just small, it is the point where small becomes insufficient as a concept. So why does this matter? Why should a scale so incredibly tiny that we can never reach it be important at all? The reason is that this is the scale at which the very idea of space itself may stop being smooth or continuous. Every physical theory we use assumes that space can be divided into smaller and smaller pieces indefinitely. It assumes distances can be measured to arbitrary precision. It assumes that time can be divided into smaller intervals without limit. But the Planck length represents a point where those assumptions fail. The energy required to probe such a region would be so enormous that space-time would collapse into a tiny black hole around the measurement. When that happens, the concept of location loses clarity. Space cannot be accessed in smaller pieces, not because our tools are insufficient, but because nature itself seems to impose a boundary. It isn't merely a curiosity. It is a central clue about how the universe may truly be built. At the scales we usually consider, space-time looks smooth. It behaves the way a continuous surface behaves. You can draw lines on it, measure angles and describe curvature. But at the Planck scale, the smooth picture seems to fall apart. The fluctuations predicted by quantum mechanics become so intense that the shape of space-time changes from one moment to the next. Instead of a steady surface, it behaves like something unsettled, perhaps not made of points at all, but built from more fundamental units that do not resemble anything familiar. In everyday life, the idea that space is smooth is something we rarely question. We assume it without thinking. When you move your hand through the air, you do not sense the microscopic details of the space between your fingers. You simply feel movement. At human scales, space-time feels so uniform that the assumption of continuity appears beyond question. Even when we shrink that picture to the scale of molecules, atoms, or smaller particles, the idea that space is a smooth background still holds. We do not observe the structure of space-time in those experiments, only the particles moving through it. But the mathematics of gravity and quantum mechanics, when combined, tell us that this smoothness must eventually break down. The Planck length is the predicted point where this breakdown occurs. This breakdown is not a chaotic fragmentation or a violent collapse. It is more like reaching a level of detail where the old description no longer applies. Think of a digital image that looks smooth and continuous from a distance. As you zoom in, the picture becomes grainy. The individual pixels begin to show, revealing that the smoothness was only an approximation. In a similar way, the Planck length may reveal a granular structure of space-time, though the nature of that granularity remains unknown. Some theories propose that space-time is made of discrete units. Others suggest that space-time emerges from relationships between more fundamental elements, not from a physical medium. And still others propose that space and time themselves may not be fundamental at all, but byproducts of deeper processes that operate without them. Yet even without knowing the precise nature of these structures, the Planck scale offers a boundary where these ideas must matter. It marks the point where the smooth description we use for space stops being reliable. It marks the limit of our ability to define distances in the traditional sense. It marks the frontier where geometry itself begins to lose meaning. All these changes emphasize why the Planck scale, despite being unimaginably small, occupies an essential place in the search for a complete understanding of the universe. Another way to appreciate this tiny scale is to examine the energies involved. The Planck energy is equivalent to compressing so much energy into such a small region that space-time curves dramatically. It's not simply a matter of reaching higher speeds or smashing particles together more violently. It is a matter of forcing nature into a state where its structure reacts with intensity. If you were to take a single particle and accelerate it to the Planck energy, the density of the energy around it would become so great that the gravitational effects would overwhelm the particle's own identity. The familiar boundaries between the particle, the energy around it, and the space through which it moves would blur. The particle would become more like a region of space-time distortion than a separate object. At that point, all the distinctions we usually rely on begin to fade. Because the Planck scale pushes us out of the world of particles and into a realm where geometry and energy merge, the structure of an atom suddenly feels incredibly simple by comparison. Atoms have electrons, orbitals, nuclei, interactions, and quantum states. But all of that exists at a scale where space remains smooth and predictable. When you compare an atom with the Planck length, it becomes clear how much structure exists in the things we call small. The atom feels enormous because so much of its behavior can be described using space-time that behaves consistently. At the Planck length, consistency is no longer guaranteed. This extreme difference in scale also influences how physicists imagine the early universe. At the earliest moments after the Big Bang, the universe was so small and dense that its size may have been near the Planck scale. This raises questions about how space-time behaved in those moments. If space-time was undergoing rapid fluctuations, then the structure of the early universe may have been profoundly different from anything that exists now. It may have been a place where matter and space were inseparable, where the boundaries between particles and geometry didn't yet exist. The enormous expansion that followed would have smoothed these fluctuations into the uniform space-time we now observe, leaving behind only faint traces of that earlier regularity. Understanding this process requires understanding what space-time is at these smaller scales. Even though the Planck length is beyond experimental reach, its significance emerges in the equations themselves. When physicists combine constants, such as Newton's gravitational constant, the speed of light, and Planck's constant, they produce a natural scale for length, time, and mass. These scales are not chosen arbitrarily. They arise naturally from the structure of the theories. This suggests that nature itself has a fundamental limit built in. If you try to explore beyond that limit, the equations turn unstable, signalling that the underlying reality requires a new kind of description. The sheer smallness of the Planck length has another important consequence. It explains why quantum gravity effects are so difficult to observe. If the scale at which these effects appear is so tiny, then ordinary phenomena will not reveal them. Particles moving through accelerators will behave according to quantum mechanics, because their energies are nowhere near the Planck energy. Astrophysical objects will behave according to general relativity, because the space-time curvature around them is too gentle to reveal Planck-scale effects. Only in the most extreme environments, such as the very early universe or near certain types of theoretical black holes, might these effects become visible. But we do not yet have access to such environments with direct observation. Despite all this, the smallness of the Planck scale does not diminish its importance. In fact, the tiny size highlights how large the universe is compared with its most fundamental structure. It reminds us that the world we experience is shaped by processes that operate across a staggering range of scales. It also suggests that the seemingly solid reality of everyday life is only one layer of a much deeper structure, one that becomes increasingly unfamiliar the closer you get to the Planck length. The idea that atoms look large compared with this scale is not meant as a curiosity. It is a reminder that the smallest building blocks we can observe rest on a foundation that is far more intricate and far more mysterious. There comes a point in this journey where the discussion can no longer rely on familiar examples or comfortable mental pictures, because the behaviours we're approaching belong to regions of physics where energy stops acting like something that merely influences matter and instead begins shaping the very environment in which matter exists. Rather than easing into this with comparisons or analogies, it may be more helpful to examine the shift directly, because the moment energy becomes concentrated enough to affect the structure of space-time itself marks one of the most important thresholds in all of physics. This is where density stops being just a property of a region, and instead becomes a force capable of bending, folding, or even collapsing the geometry around it. The first step toward grasping this transition is recognizing that energy isn't simply a number you assign to a particle or a field. In general relativity, energy plays the role of a source that determines how space-time curves. In everyday circumstances, the effect is too small to notice. A warm cup of tea has energy, but its gravitational pull is so faint that not even the most precise measuring instruments detect any curvature caused by it. Even large-scale energy distributions like those inside stars or planets produce curvature that is noticeable only across vast distances or in specific conditions. The energy that bends space-time in a meaningful way usually involves astronomical quantities, such as those found in black holes or neutron stars. But the mathematics of relativity do not place an explicit upper limit on how intense a local energy concentration can be. If enough energy is squeezed into a sufficiently small region, the curvature becomes stronger and stronger, eventually reaching a point where the equations describing that curvature begin to predict extreme effects. Now, under usual circumstances, energy is never condensed to the levels required to create those outcomes. The largest particle accelerators humanity has built fall staggeringly short of that mark. Even the most violent astrophysical phenomena such as supernova explosions do not reach it. Yet the physics still describes what would happen if that concentration did occur, and what it describes is a world that behaves very differently from the one we're used to. One of the most basic features of energy is its ability to take many forms. It can appear as kinetic energy, potential energy, thermal energy, pressure, tension, or fields. In classical physics, these variations matter because they affect how objects move or respond to forces. In relativity, however, all forms of energy influence the curvature of space-time. Whether energy comes from heat, motion, or field strength doesn't change its effect on the geometry. This universality means that as energy density rises, the influence on curvature also increases in a straightforward and unavoidable way. The equations make no distinction between different sources once you consider curvature at the fundamental level. When energy intensifies enough, the curvature grows to the point that space-time becomes noticeably distorted. This distortion isn't something that happens to matter alone. The very coordinates used to describe locations begin shifting. Light rays, which normally travel straight through space, deviate from their paths. Time intervals measured by clocks near such concentrations change their rate compared with clocks farther away. All these effects have already been observed near massive objects like stars, but the situation becomes far more dramatic when pushing the energy density to truly extreme levels. As the density rises further, one finds that space-time becomes reactive in unfamiliar ways. The geometry shifts rapidly with even small changes in energy. Instead of a smooth curve, the shape becomes something that could be described only through equations that try to track the evolving distortions. Gravity, normally the weakest of the forces, starts behaving with surprising strength at small distances, because the energy density amplifies its influence. These changes occur gradually at first, then accelerate as the density approaches levels comparable to the Planck scale. At this point, the question of defining a region becomes more complicated. In standard physics, a region of space is something you can describe by specifying boundaries, coordinates that mark where the region begins and ends. But when the curvature grows strong enough, the boundaries themselves start behaving like dynamic entities. The distances shrink or stretch, depending on the energy inside them. A small packet of energy influences the geometry so dramatically that the region containing it may compress in a way that doesn't resemble normal shrinking. It may distort into shapes impossible to visualize, because those shapes exist in space-time rather than space alone. Another difficulty appears when thinking about time. At high energy densities, the flow of time changes depending on location. Observers sitting near intense concentrations would experience the passage of time differently from those far away. Normally, this time dilation is extremely small, visible only near objects like black holes, but as the energy density grows, the effect becomes substantial even across tiny distances. Two observers separated by what we would consider an unimaginably small interval might measure time differently in noticeable ways. This variation indicates that energy doesn't just warp the shape of space, it warps the structure of time as well. If one continues raising the density, the curvature eventually reaches values so high that the equations of general relativity can no longer produce stable or meaningful results. They begin predicting singular behavior, points where curvature becomes infinite, where distances shrink to zero, or where time loses its usual order. These singularities are not meant to be taken as literal. They are signals that the theory has been pushed beyond its range of validity. But the important part is that these signals appear when energy density becomes extreme enough. They don't appear in ordinary environments. They surface only when energy reaches levels comparable to the Planck scale. These instabilities have another consequence. The slightest disturbance in such a region could produce enormous changes in curvature. If a tiny fluctuation appears in the energy, the geometry might respond disproportionately. Instead of small ripple effects, you could have profound distortions developing instantly. This sensitivity makes prediction nearly impossible using the standard equations. The mathematics start behaving chaotically because they aren't designed to track systems where space-time fluctuates so dramatically. At this point, the behavior of matter must also be reconsidered. Matter usually moves along what relativity calls geodesics, paths determined by the curvature of space-time. But when curvature becomes too large, geodesics lose their stability. Two nearby particles might start moving along paths that diverge rapidly, or converge in ways that cannot be predicted with standard models. The usual assumptions of how particles move or interact start to dissolve. It's not just that matter becomes unpredictable, it's that the environment-defining motion begins changing faster than the motion itself. Quantum physics adds another layer of complexity. In quantum mechanics, uncertainty is unavoidable. Particles fluctuate in position and momentum even under ordinary conditions. Normally these fluctuations occur against a stable space-time background, but when energy density intensifies to the point where space-time itself becomes unstable, the fluctuations amplify in unexpected ways. The uncertainty in a particle's position could become so great that it spreads across regions where the curvature is shifting at different rates. This means the particle is effectively experiencing multiple geometrical environments at once. The effect is not one we can imagine using classical terms because it lacks the stability of any known reference frame. If you then combine quantum fluctuations with extreme curvature, new challenges appear. The particle's own energy contributes to the curvature, and the curvature influences the particle's motion, creating a loop where the behavior of each shapes the other. Normally this coupling is weak. At high densities, however, it intensifies dramatically. What was once a small correction becomes a dominant factor. The theory begins predicting values that shift wildly with small changes in the initial conditions. This is another sign that the energy has reached a threshold where new rules must apply. One of the most striking consequences of dense energy is the possibility of forming miniature black holes. If enough energy occupies a small enough space, the region around it would curve so intensely that not even light could escape. This doesn't mean the energy itself becomes a classical black hole in the familiar sense. Instead, the region becomes so curved that the usual distinctions between inside and outside, past and future, or cause and effect begin to behave differently. These black hole-like formations are not stable structures. They fluctuate rapidly because the quantum uncertainty at this scale prevents the horizon from remaining fixed. The geometry becomes dynamic at a level not seen in classical gravitational collapse. All these considerations may seem challenging to visualize, and that is entirely natural. The behaviors at these scales do not resemble anything found in daily life. Even astrophysical black holes, as exotic as they are, behave in predictable ways because they exist far above the Planck scale. The energy density in their interiors may be extreme, but the mathematics describing them remains tractable for the most part. At the Planck scale, by contrast, the equations behave as if they are facing a barrier. They attempt to describe the curvature but are overwhelmed by the rapid changes in geometry caused by the dense energy. This is why physicists argue that a new theory is required to describe what really happens in such conditions. The threshold where energy warps reality so severely is not just a point of breakdown, it is the doorway to whatever deeper framework must underlie both quantum mechanics and relativity. The instability of the equations serves as a kind of beacon, identifying where that new framework must begin. Yet despite the uncertainty, the broad message from the existing theories remains consistent. Beyond a certain density, space and time cannot be treated as smooth or continuous. They must arise from something more fundamental. The ultimate significance of this point is not limited to theoretical puzzles. It has implications for cosmology, for the earliest moments of the universe, and for understanding how physical laws emerge from deeper principles. When the energy density in the early universe was extraordinarily high, the entire fabric of space-time may have existed in a state where these effects mattered. The smoothness of the universe we see today could be the result of an expansion from a phase where energy warped reality so intensely that space-time did not have a stable structure. The transition from that state to the one we inhabit now may hold the answers to many unresolved questions in cosmology. There is a point in physics where the universe stops offering suggestions and instead places an unmistakable boundary in front of anyone attempting to push deeper. It's not a physical barrier like the surface of a wall or a cliff edge, nor is it a warning delivered through dramatic events. Instead, the limit shows itself through mathematics that fail to stabilize, through concepts that lose their meaning, and through predictions that unravel no matter how carefully one prepares the equations. This boundary is tied to the Planck energy. It represents the combination of conditions where gravity, quantum mechanics, and space-time geometry all demand to be considered together, yet refuse to cooperate under the rules we currently possess. Although the universe remains entirely silent on the matter, the behaviour of its laws makes the message clear enough. This is as far as current theories can go without breaking. Understanding why this boundary exists requires examining what happens when you attempt to probe increasingly powerful interactions. In most areas of physics, turning up the energy simply reveals smaller structures or more detailed processes. A microscope lets you examine cells, then smaller versions let you inspect molecules. Particle accelerators increase energy to explore atomic nuclei and smaller constituents. Each new level reveals finer details because the tools interact with matter at stronger energies and therefore shorter length scales. This progression may create the impression that one could continue indefinitely, shrinking the scale of investigation by steadily increasing the energy. It seems reasonable to assume that nature has no preference regarding how small we look. But that assumption begins to dissolve once energies approach the Planck scale. The key idea is that distance and energy are linked through quantum mechanics. If you want to measure a smaller region, you must use particles or waves with shorter wavelengths, and shorter wavelengths require higher energies. This relationship works perfectly well at familiar scales, enabling modern particle physics. However, the more energy you concentrate into a small region, the more mass energy density you create. According to general relativity, energy density affects the curvature of spacetime. If you keep increasing the energy, the curvature grows in proportion to that increase. Eventually, the curvature becomes so strong that the region collapses into a microscopic black hole. Instead of revealing structures smaller than the chosen scale, the act of measurement eliminates access to the region altogether. The Planck energy marks the moment where any further attempt to probe smaller distances leads directly to gravitational collapse. This relationship, energy trying to reveal smaller scales while gravity prevents them, creates a self-limiting boundary imposed by nature itself. The universe does not permit inspection of regions smaller than the Planck length by using energies greater than the Planck energy. This is where the notion of a universal do-not-cross sign arises. It is not a barrier created through force but through contradiction. The theories describing the world refuse to allow deeper probing without replacing themselves entirely. Another way to see the boundary is through the failure of field theories at extreme energies. Quantum field theory, the framework used to describe particle interactions, begins to require infinite numbers to complete its calculations when energies near the Planck scale. These infinities are different from the manageable divergences that renormalization techniques can tame. Instead, they grow uncontrollably, making results meaningless. The failure isn't due to technical difficulty, it's due to the structure of the theory being incompatible with gravity at such densities. Quantum field theory assumes a fixed space-time background, but the gravitational effects at the Planck scale prevent any background from remaining fixed. Without a stable environment in which particles move, the theory cannot function. The energy scale where this breakdown occurs aligns with the Planck energy, providing yet another indicator that something fundamental limits our approach. General relativity, on the other hand, struggles for a different reason. Its equations assume that spacetime is smooth and continuous, capable of being divided into arbitrarily small pieces. But quantum mechanics imposes uncertainty on all physical quantities, including those that define spacetime itself. As energy density increases, the fluctuations in spacetime grow strong enough that the smoothness assumption collapses. Distances can no longer be meaningfully defined, and the curvature becomes unpredictable. The mathematics begin producing singularities, points where curvature becomes infinite or undefined, well before any real physical singularity is formed. These singularities are not taken literally. They describe a theory encountering conditions that it cannot meaningfully represent. Here again, the Planck energy emerges as the threshold where this failure becomes unavoidable. It is rarely appreciated how remarkable it is that the same energy scale appears in both branches of physics. The Planck energy arises independently in quantum mechanics and in relativity through combinations of fundamental constants. Quantum mechanics contributes Planck's constant, relativity contributes the speed of light, and Newton's gravitational constant. These constants define the smallest meaningful length, time, and mass. The fact that this boundary emerges without any arbitrary choices shows that it is woven into the structure of the universe rather than imposed by human preference. If you change any of the constants, the Planck scale adjusts accordingly. It is a natural consequence of the rules rather than an artificially defined threshold. There's another important question tied to this boundary. What happens to the familiar concepts of force and matter when energies reach this extreme? Normally, the forces of nature behave differently at different energy levels. Electromagnetism, the weak interaction, and the strong interaction change their strengths gradually as energy increases. In some theories, these forces converge toward a unified description at very high energies. But as you approach the Planck energy, the presence of gravity complicates everything. Gravity, usually the weakest force, grows in influence because the energy density becomes enormous. It rises so rapidly that it eventually pulls the other interactions out of the domain where their usual descriptions work. If you were to imagine increasing energy indefinitely, the forces might merge in ways predicted by grand unified theories. But gravity prevents that unlimited increase by destabilizing spacetime itself. This effect prevents experiments from accessing the region of energy, where certain theories expect deeper symmetries to appear. That makes the Planck scale not just a physical threshold, but an experimental one. It locks away an entire region of physics that might contain unifying principles or deeper structures. In a sense, the universe keeps its most fundamental behaviors hidden behind conditions that cannot be accessed without violating the structure that makes investigation possible. This doesn't necessarily mean the deeper structure is unknowable. It simply means the path to discovering it cannot rely on traditional approaches that probe smaller and smaller scales with higher and higher energies. Another aspect of this boundary comes from the behavior of measurement at extreme conditions. Measurement in physics is not just an act of observation, it requires interaction. To measure a small region, one must send energy into it. At everyday scales, that interaction introduces only tiny disturbances. But at the Planck scale, the disturbance becomes so large that the act of measurement significantly modifies the region being studied. This is not due to limitations in apparatus design. It's a consequence of the laws of physics. The uncertainty principle predicts that measurement requires energy. Relativity predicts that energy curves space-time. Combining these predictions means that the measurement alters the shape of the region so dramatically that it prevents any meaningful result. At the Planck scale, measurement becomes self-defeating. This limitation influences how physicists interpret models involving spacetime at the smaller scales. If direct measurement is impossible, any new theory must be formulated in terms that do not rely on probing below a certain threshold. This does not mean science stops. It means science must shift its strategy. Instead of attempting to resolve smaller distances directly, physicists search for indirect signatures, such as remnants from the early universe, gravitational effects in extreme environments, or mathematical consistency across multiple theories. The Planck scale becomes a guide rather than an endpoint, pointing toward the conditions where new physics must appear, even if those conditions cannot be reached experimentally. The idea of a do-not-cross sign gains more meaning when you consider how rare fundamental limits are in physics. Many quantities that feel absolute are not truly absolute. Temperature has no strict upper limit except under specific interpretations. Velocities can approach the speed of light but never exceed it, making that a fundamental limit in relativity. The Planck energy is another limit, not because crossing it is forbidden by force, but because the theories that define energy, space, and time all stop functioning beyond that threshold. The universe itself offers no coherent definitions beyond this boundary. You cannot meaningfully describe space smaller than the Planck length, or intervals shorter than the Planck time, because the geometry required to define them can no longer be constructed. Recognizing this limit helps explain why attempts to unify quantum mechanics and gravity have proven so difficult. Each theory works beautifully in its own domain, but neither can extend into the other's domain without faltering. The Planck scale marks the seam where these two domains meet and where their incompatibilities become undeniable. Theories such as string theory, loop quantum gravity, causal dynamical triangulations, and others attempt to bridge this seam by proposing new fundamental structures. Some propose that space-time is made of discrete units. Some propose that strings or loops replace point-like particles. Others propose that space-time emerges from deeper relationships rather than existing independently. All these ideas attempt to address the failures that occur at the Planck energy, and while none have yet achieved universal acceptance, they illustrate the need for a theory that does not break at this threshold. Another perspective on this boundary comes from cosmology. In the earlier stages of the universe, the energy density may have been near the Planck scale. If that is the case, the initial moments of cosmic history lie behind this do not cross sign. We cannot describe those moments using general relativity, because curvature would have been too extreme. We cannot describe them using quantum field theory because quantum fluctuations would have been too large. Whatever conditions existed at that time require new laws. The Planck energy marks not only a physical limit, but a historical boundary. Anything before it remains speculative until a new theory can handle the conditions. Despite the challenges this boundary presents, it does not represent an obstacle in the negative sense. Instead, it functions like the edge of a map where the next region awaits definition. Physics has reached many such edges before. The classical world ended in uncertainty until quantum mechanics arrived. Newtonian mechanics faltered at high speeds until relativity clarified the situation. Each boundary marked an opportunity for new insights. The Planck scale may represent the next such frontier. It can be difficult to accept that the calm, steady space-time we experience every day might conceal a restless interior beneath its surface. Most of the time, nothing about the world suggests that the fabric of reality is unstable. You walk across a room, and the distance remains the same. You set a clock on a table and it ticks without any sign that time is flickering or reshaping itself. Every measurement you perform, whether in daily life or in a laboratory, relies on the assumption that space-time is smooth and dependable. Yet, when you investigate the predictions made by quantum mechanics combined with gravity, another picture begins to form, one that describes not a stable framework, but an underlying layer filled with fluctuations so extreme that ordinary descriptions collapse. Physicists refer to this restless underlying layer as quantum foam, and it becomes unavoidable when energies approach the Planck scale. The phrase quantum foam might evoke an image of something frothy or chaotic, but the idea is not meant to evoke a dramatic or violent picture. Instead, it refers to the way space-time behaves when quantum fluctuations become large enough to dominate its structure. Normally, space-time appears flat or gently curved depending on the mass and energy present. At atomic scales and even far smaller ones, the curvature remains smooth. But at length comparable to the Planck length, quantum fluctuations influence space-time so intensely that it stops being smooth. Instead, it becomes a shifting pattern of constantly changing geometries. What looks stable at ordinary scales emerges as a dynamic surface when magnified far enough. This shift in behavior arises because quantum mechanics demands uncertainty in all measurable quantities. Position and momentum cannot be known with infinite precision. Energy and time also share an uncertainty relationship. These uncertainties exist at every scale, but their effects are negligible in most environments. Only when energy is confined to a region tiny enough that quantum effects become dominant do these uncertainties rise to a level that influences the geometry of space-time itself. At those scales, tiny fluctuations in energy density distort space-time in brief, intense bursts. These bursts are not sustained, nor do they propagate in ways familiar from larger-scale gravitational waves. They appear momentarily, influencing curvature and then fading, only to be replaced by new ones. This constant, unpredictable shifting is what differentiates quantum foam from the smooth geometry described by relativity. Instead of treating spacetime as something like a continuous sheet, the foam picture suggests that its structure cannot be subdivided indefinitely into smaller and smaller pieces. At some point, the smooth description loses meaning. The idea of a line, a surface, or a volume no longer fits. Instead, you have a collection of temporary geometries popping in and out of existence due to quantum fluctuations. A natural question arises when considering this picture. If space-time is so active at the smallest scales, why doesn't this turmoil appear in everyday observations? The answer is that the fluctuations cancel out at larger scales. Just as the random motion of air molecules becomes smooth airflow at human scale, the random geometric fluctuations of quantum foam average out into a stable spacetime at scales far larger than the Planck length. The apparent calmness of the world is a statistical outcome of countless fluctuations that reinforce and cancel each other. Only when probing extremely small regions or when extreme energies compress spacetime enough do the fluctuations become impossible to ignore. One of the intriguing consequences of this fluctuating structure is that the notions of distance and time lose their usual meaning. In classical physics, distances are defined through the geometry of spacetime, which is assumed to remain stable when measuring a region. But at the Planck scale, the geometry changes so quickly and so dramatically that defining a distance becomes ambiguous. The curvature shifts before any measurement could be made. A length measured at one moment might differ from the length measured an instant later, because the geometry has changed. This dynamic nature of spacetime means that the concept of a fixed metric, the mathematical object that defines distances, breaks down. There is no stable background from which to reference a measurement. Time faces a similar difficulty. In relativity, time is part of the geometry of spacetime, influenced by the curvature of that geometry. When that curvature fluctuates violently, the flow of time becomes ill-defined. Two events separated by tiny intervals cannot reliably be assigned a consistent temporal order. The uncertainty in the geometry injects uncertainty into the temporal sequence. At everyday scales, this effect is vanishingly small, but near the Planck scale, it becomes significant enough that the idea of time as a continuous ordered flow loses its footing. All of this suggests that space-time at the Planck scale behaves less like a continuous fabric, and more like a series of temporary configurations. Each configuration appears briefly, shaped by the quantum fluctuations that create it, and then disappears, giving rise to another configuration with different properties. These constant transitions create something that behaves more like an underlying process than a structure. Space-time becomes something dynamic, not a fixed arena, but an ever-changing pattern shaped by quantum laws. This picture challenges some of the assumptions that have guided physics for centuries. Much of classical physics, and even relativity, rests on the belief that space and time exist independently of the objects within them. They serve as the stage on which events unfold. But if quantum foam is real, it suggests that the stage itself is not stable or fixed. Instead, it is both influenced by and influencing the quantum processes occurring within it. The boundaries between the stage and the actors blur, because the stage is partly created by the actors. Understanding this foam-like behaviour is not simply a matter of curiosity. It provides essential clues about the nature of any deeper theory that must unify quantum mechanics and gravity. Any theory that attempts to describe reality at the Planck scale must account for the fact that space-time loses its smooth structure. The theory must be built from entities more fundamental than the geometry of spacetime itself. That geometry must emerge from the deeper structure rather than being an ingredient of the theory. This has motivated approaches that treat spacetime as emergent rather than fundamental. One approach proposes that spacetime arises from the entanglement patterns of quantum states. If true, then the geometry we observe at large scales would be the macroscopic result of entanglement relationships that exist at the smallest scales. These relationships would determine the curvature, structure, and connectivity of space-time. A fluctuation in entanglement would correspond to a fluctuation in geometry, providing a possible explanation for the foam-like variability at the Planck scale. Another direction considers space-time as composed of discrete units. Rather than being infinitely divisible, space-time would consist of minimal building blocks, much like atoms in a material. These blocks would be incredibly small, far below the scale of any imaginable experiment, but they could combine to form the smooth geometry at larger scales. Quantum foam would then reflect the rapid, random rearrangement of these building blocks. The fluctuations would be a natural part of their behaviour rather than something that only emerges at high energies. There are also theories that describe space-time as a network or graph, where the connections between nodes define the geometry. In such models, the foam-like behaviour emerges from the changing connectivity between nodes. The geometry is not something fixed, but something that arises from the relationships in the network. Quantum fluctuations would cause the connections to shift over time, producing the irregularities associated with the foam. Despite their differences, all these theories share a common idea. The geometry of space-time cannot be fundamental. It must result from deeper principles. This insight comes directly from the recognition that smooth geometry breaks down at the Planck scale. Quantum foam is not simply a prediction of quantum gravity. It is one of the strongest indicators that the geometry we observe is a macroscopic approximation of something more complex. If one examines the nature of energy at the Planck scale, another layer of the foam-like picture emerges. Quantum field theory predicts that even empty space contains fluctuations due to the uncertainty principle. Virtual particles appear and disappear rapidly, borrowing energy from the vacuum in fleeting exchanges that usually average out. At larger scales, these fluctuations play subtle roles, influencing phenomena like the Casimir effect. But at the Planck scale, the energy involved in these fluctuations is large enough to warp space-time in noticeable ways. Each virtual particle contributes a tiny distortion. Combined, these distortions create the shifting landscape of quantum foam. This continuous creation and annihilation of virtual particles means that energy density varies rapidly across the foam. These variations influence the curvature of space-time. The geometry responds instantly to the fluctuations, generating a pattern of constant change. This is not turbulence in the classical sense, because turbulence requires a fluid and a set of forces acting on that fluid. In the foam model, the turbulence reflects the quantum processes that shape and reshape space-time at unimaginably small intervals of time. When you consider how quickly these fluctuations occur, the picture becomes even more challenging. The Planck time, the shortest meaningful interval, is incredibly small. Within each Planck time, the geometry of space-time can shift drastically. The fluctuation patterns may not form a continuous sequence, because continuity itself loses meaning at that scale. Instead, one might imagine a system where geometries transition between discrete configurations in rapid succession. Each configuration briefly defines the structure of space-time before being replaced by another. Although these ideas help describe what might happen at the Planck scale, they do not provide a complete picture. They indicate what current theories cannot explain, and why new theories are needed. The foam concept is not a final answer. It is a placeholder that acknowledges the unpredictable nature of space-time at extreme scales. Physicists use it to express how far the classical ideas of geometry must be stretched, and where quantum mechanics must take over. The impact of quantum foam extends beyond theoretical boundaries. It influences interpretations of cosmology, black hole physics, and the behaviour of particles in extreme environments. For example, the early universe may have existed in a state where quantum foam dominated the structure of space-time. If so, the initial conditions that set the stage for cosmic evolution were shaped by the foam. This idea could provide insight into the uniformity of cosmic background radiation and the initial distribution of matter. In black hole physics, quantum foam may play a role near the event horizon. where curvature becomes extreme and quantum fluctuations grow significant. Some proposals suggest that the classical picture of a smooth horizon might break down at the Planck scale, replaced by a structure influenced by foam-like behaviour. This could have implications for the information paradox and the nature of Hawking radiation. All these areas highlight why the Planck scale is considered one of the most important boundaries in physics. It marks the region where our familiar descriptions lose meaning, and where the foam-like nature of space-time must be accounted for. It serves as the interface between what we can describe confidently and what remains hidden behind the limitations of our current theories. Most discussions about the universe are able to keep gravity and quantum mechanics comfortably separated, as if they prefer staying in different corners of the theoretical world. Gravity takes responsibility for planets, stars, galaxies, and the curvature of space-time itself. Quantum rules manage the invisible realm of particles, probabilities, and microscopic interactions. They rarely intrude on one another because the circumstances where both become equally important are extraordinarily uncommon. Yet the closer we move toward the Planck energy, the more unavoidable their overlap becomes. Conditions tighten in a way that makes it impossible for either theory to ignore the other. The system demands both at once, but their assumptions refuse to fit together neatly. This is the room where both rules collide, and where our current understanding begins to show its deepest limitations. Before exploring why their coexistence becomes problematic, it is useful to consider how different these two frameworks truly are. Quantum mechanics treats particles not as solid points, but as states spread across space. A particle does not have a single trajectory. It has a wave function describing probabilities. Measurements collapse these probabilities in specific ways. Quantities like position, momentum, and energy come with unavoidable uncertainties. This probabilistic structure is not optional. It forms the foundation of quantum behaviour at every scale where the theory applies. Gravity, however, behaves in an entirely different fashion. In general relativity, mass and energy determine how space-time bends. Objects follow paths determined by that curvature. There is no probabilistic element in the geometry. A planet orbiting a star follows a geodesic trajectory, a path defined by the curvature around it. If you know the curvature and the planet's initial position, you can determine its path exactly. Unlike quantum theory, relativity relies on a smooth, continuous space-time. Measurements assume that distances and times can be made arbitrarily precise, limited only by technology, not by nature. Because these two frameworks describe different domains, physicists normally apply them separately. Quantum rules govern the very small. Relativity governs the very large. For many situations, this separation works perfectly. Atoms behave according to quantum mechanics. Solar systems behave according to relativity. There is no contradiction because the scales involved are so different that each theory remains in the region where it excels. Issues arise only when a system requires both descriptions at once. Consider a particle with enough energy that it significantly warps the space-time around it. In that case, you must apply relativity to describe the curvature. But the particle also has quantum fluctuations in its position, and momentum, meaning its gravitational field should fluctuate as well. Classical relativity cannot handle this, because it assumes the mass-energy distribution is smooth and well-defined. Meanwhile, quantum mechanics cannot describe the gravitational field, because it assumes space-time is fixed and unaffected by quantum fluctuations. Each theory needs the other to remain stable, but neither is built to accommodate that need. These tensions remain hidden until energy reaches scales where the gravitational effects of quantum fluctuations become large. That is precisely what happens at the Planck energy. At this point, the energy carried by a particle is so intense that its gravitational field becomes comparable in significance to the quantum behaviour of the particle itself. The particle's position fluctuates, so the curvature fluctuates. The particle's energy fluctuates, so the geometry fluctuates. Relativity would normally compute curvature using stable inputs. Quantum mechanics refuses to provide stable inputs. The two frameworks clash, not through a contradiction in mathematics, but through incompatible assumptions about what the inputs represent. The incompatibility becomes clearer when thinking about how each theory defines a state. In quantum mechanics, the state of a system is a wave function or a quantum field configuration. It evolves according to probabilities. Relativity treats the state of space-time as a geometric configuration determined by the energy and momentum present. There is no room for probabilities in that geometry. The curvature is not uncertain, it is exact. But at the Planck scale, the energies involved introduce uncertainties so large that the curvature must be probabilistic as well. The theory has no way to include that. It cannot treat geometry as something with fluctuations. Attempts to combine the two theories directly encounter another difficulty. Quantum mechanics allows particles to exist in superpositions, states where they do not occupy a single location or possess a single momentum. If a particle exists in a superposition of two locations, its gravitational field should also exist in a superposition of curvatures. But relativity cannot handle superposed geometries. The concept does not exist in the theory. The Einstein field equations require a definite curvature at every point. Superpositions of geometries do not solve the equations, they break them. This problem is particularly striking when thinking about time. Quantum mechanics treats time as an external parameter, something that flows uniformly. Relativity treats time as part of the geometry, something that changes when curvature changes. If the curvature fluctuates due to quantum uncertainties, then time itself must fluctuate. But quantum mechanics does not permit fluctuations in time. It requires a stable time parameter to define evolution. Without that stable time, the Schrödinger equation cannot operate. If the curvature changes randomly, the rate at which time flows becomes unpredictable. The evolution of the wave function becomes ill-defined. The same conflict appears when considering the energy required to probe small distances. As earlier sections discussed, probing a smaller region requires higher energy. But as the energy rises, the curvature increases. Eventually, the curvature becomes strong enough that the region collapses under its own gravitational effects. This collapse is something relativity predicts clearly. Yet quantum mechanics insists that the particle representing the probe still has a probability distribution, not a definite location. In relativity, the collapse occurs in a definite region. In quantum mechanics, the region is not definite. The collapse cannot be described consistently in both frameworks. One must define the region in a single way, yet the theories demand different definitions. An even more subtle difficulty emerges when thinking about vacuum energy. In quantum field theory, the vacuum is not empty. It contains constantly fluctuating fields with associated energy densities. On average, these fluctuations cancel out or contribute only small effects. But relativity responds to energy regardless of whether the energy comes from particles, fields, or the vacuum. If the vacuum contains enormous fluctuations, then the curvature should fluctuate accordingly. Yet we do not observe such curvature at large scales. The vacuum appears gravitationally neutral. Some unknown mechanism must suppress the gravitational influence of vacuum energy, or the theory must describe vacuum fluctuations in a way that does not correspond to classical energy. Neither explanation exists in a settled form. All these issues converge near the Planck scale because the fluctuations become too large for either theory to ignore. Quantum mechanics does not stop producing uncertainties simply because gravity becomes important. Gravity does not become less responsive simply because the uncertainties grow large. Both continue operating according to their rules, but the rules contradict one another when both apply simultaneously. The Planck energy is therefore the point where the collision between the two becomes unavoidable. To appreciate how difficult this collision is, it helps to examine the mathematical structures of the theories. Quantum mechanics describes systems through operators acting on Hilbert spaces. These operators correspond to observables like position or momentum. Relativity describes systems through differential geometry and tensor calculus. The Einstein field equations relate curvature to the energy-momentum tensor. These two mathematical languages have almost nothing in common. One handles uncertainty and linear combinations of states. The other handles continuous smooth geometries with deterministic evolution. Merging them requires reformulating one or both in radically different terms. One of the earliest attempts to combine them was to quantize gravity directly by treating curvature as a quantum field. This approach tries to define a graviton, a hypothetical particle that carries the gravitational force in the same way photons carry electromagnetism. But this approach leads to divergences that cannot be renormalized. The corrections required to define the theory at small distances become infinite, and no method exists to cancel them. Unlike electromagnetism or the strong interaction, gravity grows too quickly at high energies for the perturbative approach to work. These failures are technical in form but conceptual in significance. They signal that treating gravity as another force is insufficient. A different attempt involves modifying relativity. Instead of treating spacetime as continuous, some theories treat it as composed of discrete units. If spacetime is not continuous, then the fluctuations predicted by quantum mechanics might have natural cutoffs. Distances smaller than the Planck length would have no meaning. Time intervals shorter than the Planck time would not exist. Under this view, the geometry would emerge from discrete building blocks, much like crystal structure emerges from atoms. But even this approach faces challenges. The discrete units must still produce the smooth space-time we observe at large scales. They must also interact in ways that match quantum predictions. Achieving both goals simultaneously has proven extremely challenging. Another set of theories takes a different direction entirely. Instead of starting with space and time, they begin with information, entanglement, or abstract mathematical relationships. The idea is that space-time emerges from deeper principles. If true, then gravity would not be a force in the usual sense. It would be a large-scale effect arising from microscopic interactions. Quantum rules would not collide with gravity, because gravity would be an emergent phenomenon that incorporates quantum principles from the start. This approach avoids many of the contradictions, but it remains incomplete and lacks the experimental support needed to elevate it from speculation to accepted theory. Despite the lack of a unified theory, the collision between gravity and quantum rules provides essential information. It tells us where new physics must appear. It tells us which assumptions cannot remain untouched. It reveals which mathematical structures fail and why they fail. The Planck energy is not a boundary defined by convenience. It is the point where the limitations of our theories become undeniable. Some of the most compelling clues about this collision come from the behavior of black holes. At the horizon of a black hole, curvature becomes large, but not yet infinite. Quantum effects near the horizon produce Hawking radiation, a phenomenon that depends on both quantum mechanics and gravity. The existence of Hawking radiation suggests that quantum field theory can be applied on curved spacetime, at least under certain conditions. But as one approaches the interior, the curvature grows beyond the domain where this hybrid description works. The equations begin predicting contradictory outcomes. Information flow becomes problematic. The compatibility between quantum unitarity and relativistic geometry breaks down. These issues reflect the same tension found at the Planck scale. The event horizon of a small black hole may be only a few times larger than the Planck length. Quantum fluctuations near the horizon may significantly influence the geometry. Black hole evaporation raises questions about whether information is destroyed or preserved. The conflict between the two theories appears again in a different form, highlighting the need for a new framework. Another example comes from the early universe. During the first fraction of a second after the Big Bang, energy densities were extraordinarily high. Quantum fluctuations likely shape the distribution of matter and radiation. Gravity also played a major role because the universe was dense enough that curvature changed rapidly. The combination of these two influences means that the earliest moments of the universe existed in the domain where gravity and quantum mechanics collided. The smooth universe we observe today emerged from a phase where the geometry fluctuated in ways we cannot describe with current theories. One might wonder whether the collision between gravity and quantum rules could be avoided by redefining the domain where each theory applies. Perhaps quantum mechanics should not be applied to gravity. Perhaps relativity should not be applied to quantum systems. But both theories have been tested extensively in their respective domains. Neither shows signs of failure under the conditions where they are meant to apply. The failure appears only when both are required simultaneously. This suggests that neither theory is fundamentally incorrect. Instead, each describes an aspect of a deeper structure not yet fully known. That deeper structure must accommodate both quantum uncertainty and gravitational curvature. It must operate at scales where geometry fluctuates and where energy influences space-time even in its smallest configurations. It must provide a description of reality where the probabilistic nature of quantum events and the geometric nature of gravity coexist without contradiction. Whatever theory accomplishes, this will be the one that explains what truly happens when gravity and quantum rules occupy the same room. Trying to understand matter at ordinary scales is already a challenge, but the rules guiding that behavior are at least recognizable. Particles can be categorized, forces can be listed. Their interactions, however subtle, usually fall into patterns that physicists know how to follow. Yet once the energy rises toward the Planck scale, many of these familiar patterns no longer hold their shape. The distinctions that make particle physics workable begin to loosen. Quantities that once remained separate start merging into something harder to classify. The world of well-defined particles and clear-cut forces begins shifting into a domain where neither category behaves as expected. Instead of discrete actors and distinct interactions, you find something closer to a set of relationships that constantly reshuffle themselves as the energy intensifies. To get a sense of how drastic this shift becomes, it's helpful to consider how particles are normally described. At accessible energies, each particle has a clean identity. Electrons behave in predictable ways. Quarks combine to form protons and neutrons. Neutrinos pass through matter with slight interactions. The fundamental forces act upon these particles differently, and their roles remain firmly separated. Electromagnetism governs charged particles. The strong force binds quarks. The weak force handles processes like radioactive decay. Gravity affects everything but is so feeble at particle scales that it can be safely ignored. These divisions allow scientists to build models that categorize particles and their behavior with remarkable precision. However, these models rely on the assumption that particles remain distinct and that the forces acting on them can be treated independently. As energies grow higher, especially when approaching the region where gravity cannot be neglected, the clarity begins to break down. One of the first signs comes from the way particle masses respond to increasing energy. Mass, as described by quantum field theory, is not a fixed property. It depends on interactions with the surrounding fields, like the Higgs field, which gives certain particles their mass. These interactions grow stronger or weaker depending on the energy scale. At low energies, the masses remain stable, but as the energy increases, especially far beyond accessible experimental regimes, these masses begin shifting. They do not remain constant. Some decrease, some begin to unify. The distinctions between particle types grow less sharp. Another shift occurs in the relative strengths of the forces. At low energies, the strong force is the most powerful, followed by electromagnetism, then the weak force, and finally gravity trailing far behind. But the strength of each force varies depending on the energy of the environment in which the particles interact. As the energy increases, the strong force weakens. The electromagnetic and weak forces begin converging. The weak force grows stronger relative to electromagnetism, and at extremely high energies still far below the Planck scale, The strong, weak, and electromagnetic forces may converge into a unified interaction. This is not speculation, but a result of extrapolating the renormalization behavior of the forces. Yet this unification is not fully achieved before gravity becomes too strong to ignore. As energy approaches the Planck scale, gravity quickly overtakes the other three forces. Instead of allowing them to merge neatly, gravity disrupts the process by introducing curvature, fluctuations, and instabilities. The attempt to unify the forces is interrupted by the emergence of gravitational effects that dominate the dynamics. It is not that the forces stop converging, they continue following the mathematical trends predicted, but the growing strength of gravity overshadows them in a way that makes their unification impossible to observe using the frameworks currently available. This interference changes how particles behave as well. At moderate energies, each particle can be treated as an excitation of its corresponding field. The electron is a mode of the electron field. Photons are excitations of the electromagnetic field. The gluons correspond to the strong force, but these descriptions rely on the fields existing on a stable spacetime. When spacetime fluctuates, the fields fluctuate as well. The excitations begin mixing, not in the way particles mix through weak or strong interactions, but through the shifting curvature that affects all fields simultaneously. The gravitational influence scrambles the distinct field identities, making it harder to define what counts as a particle under such conditions. Even in more familiar high-energy environments, like those studied in particle accelerators, certain effects already hint that particle identity is more flexible than it seems. Neutrinos can oscillate between different types as they travel. Quarks cannot be isolated because the strong force increases dramatically at larger distances, pulling them back together. In these cases, identity is contextual rather than absolute. At the Planck scale, this context sensitivity becomes even more pronounced. The particles blur enough that the idea of a distinct entity moving through space stops being reliable. If one attempts to examine a particle's position under these conditions, the uncertainties grow large enough that the particle's wave function may spread across regions influenced by different curvatures. The particle becomes not a point or even a cloud, but a probabilistic distribution moving through a geometry that itself is uncertain. Because of the strong interplay between energy and curvature, the geometry influences the particle's behavior, and the particle's behavior influences the geometry. Particle identity becomes obscure because the environment defining it is unstable. Another issue arises when thinking about interactions. Under normal conditions, interactions occur at specific points, governed by the coupling strengths of the forces. Calculations involve careful tracking of these interactions through Feynman diagrams or other quantum field theory tools. But those calculations depend on a stable background and treat interactions as additions to that background. At the Planck scale, interactions cannot be treated as minor contributions. They dominate the system. They distort the surrounding space so profoundly that the interaction becomes inseparable from the geometry. Distinct forces lose their independence. The curvature created by the energy of one interaction affects the behavior of another, leading to feedback loops that cannot be separated into individual components. Take, for example, the electromagnetic and strong forces. At high energies, they both influence particle behavior, but their equations remain distinct. Each involves separate fields, separate symmetries, and separate kinds of charges. But gravity responds to energy in all of these interactions, regardless of the specific force involved. As energy increases, the gravitational response becomes stronger than the interactions themselves. Instead of multiple forces acting separately, the dominant effect becomes the geometry shaped by all energy sources together. The result is a blurring of forces driven by gravity's increasing influence, not by the internal structure of the quantum fields. In some speculative frameworks, this blurring has an even deeper meaning. It suggests that particles and forces are not fundamental features of the universe but emergent behaviors. In these frameworks, particles are patterns in deeper mathematical structures. Forces are ways that these patterns respond to changes. When energy becomes extreme, the patterns shift in ways that reveal their shared foundation. This would make the merging of forces not an anomaly, but a sign that we are approaching the underlying structure of reality. The Planck scale would then represent not simply the limit of our theories, but the doorway to the processes that generate the familiar particles and interactions at lower energies. This idea is supported indirectly by the behavior of symmetry at high energies. In particle physics, symmetries guide how interactions occur. The more energy a system has, the more these symmetries reveal themselves. At high energies, certain broken symmetries become restored, meaning that distinctions seen at low energies disappear. This restoration of symmetry suggests that at even higher energies, perhaps closer to the Planck region, more distinctions could fade. Particles that appear different at low energies might emerge as different manifestations of the same underlying structure. The equations describing forces also change dramatically as energies increase. Their coupling constants, the numbers that describe the strength of each interaction, shift according to the details of renormalization. These constants represent how strongly particles influence one another. At extremely high energies, the couplings of the strong, weak, and electromagnetic forces appear to converge. This convergence indicates that their independence may be an emergent feature of low-energy physics rather than a permanent division, but the convergence never becomes exact within the standard model. New physics would be required to extend this pattern beyond its limits, and gravity interrupts the process before experiments can reach that point. The blurring of particles and forces is also connected to how field excitations behave when subjected to intense curvature. In ordinary conditions, fields remain relatively stable even when perturbed. They maintain their structure across space and time, but at Planck scale energies the curvature becomes so strong that the field lines themselves distort. A field becomes difficult to define consistently because it relies on geometric assumptions that no longer apply. Particles become harder to interpret because the excitations that define them depend on the stability of the field. Without that stability, the field's modes lose their distinct signatures. A particle, in such an environment, becomes a fluctuating pattern in a fluctuating medium. There are also implications for concepts like charge, spin, and quantum numbers. These properties help classify particles and determine how they interact. At ordinary scales, they remain consistent and measurable. But if the underlying field structure becomes unstable, the meaning of these quantum numbers may shift. For example, the concept of spin relies on spacetime symmetries. If spacetime itself becomes unstable, the meaning of spin becomes ambiguous. Charge depends on the structure of gauge fields, which also rely on stable geometry. Near the Planck scale, these definitions may lose their reliability. One of the more challenging consequences of this blurring is the potential breakdown of locality. In both quantum mechanics and relativity, locality plays an essential role. It defines how interactions occur at specific points in spacetime. But when particles and forces blur together, the idea of an interaction occurring at a precise location becomes difficult to support. The region over which the interaction takes place shifts as curvature fluctuates. Quantum uncertainty spreads particles across regions with different geometries. Interactions become non-local in ways that defy simple interpretation. Another facet of this issue involves virtual particles. These transient entities appear in quantum field theory as mathematical consequences of uncertainty. They exist briefly and contribute to interactions. At ordinary energies, they play subtle roles. But at the Planck scale, their contributions grow massive. Virtual particles with enormous energies appear momentarily, distorting space-time in ways that cannot be ignored. The foam-like geometry changes rapidly, and the distinction between real and virtual particles becomes blurred. The energy they carry can affect curvature to the point that the environment no longer supports the usual categories of particle identity. If one steps back and considers this environment more broadly, The picture resembles a domain where the familiar subatomic world dissolves into something shaped by relationships rather than objects. Forces lose their boundaries, particles lose their clear identities, and the geometry of space ceases to remain a passive background. Everything becomes interdependent. Energy shapes geometry, geometry shapes particles, particles shape forces. The interactions between all three cannot be separated. They no longer exist as independent aspects of reality, but become intertwined elements of a more fundamental structure. This merging of roles suggests that the Planck scale is not simply a place where theories fail. It is a place where distinctions that make sense at low energies stop being relevant. The idea that particles are discrete units becomes an approximation. The idea that forces act separately becomes a simplification. The idea that spacetime is a stage becomes an emergent feature. At lower energies, these approximations and simplifications work extraordinarily well, producing the physics we observe. Near the Planck scale, they break down, revealing that the universe may not be built from independent particles and forces, but from something deeper that manifests as particles and forces under more ordinary conditions. Few ideas in physics seem as intimidating as black holes, yet the version familiar from astronomy is not the only form they can take. The moment energy becomes concentrated into a region small enough, gravity responds with surprising strength, even if the amount of energy involved is microscopic by everyday standards. When the energy density rises far enough, the resulting curvature becomes so intense that spacetime behaves as if a tiny horizon forms around the region. In ordinary life, this never occurs. Even the most energetic events we observe are nowhere near the threshold required. But the environment near the Planck scale allows this possibility to emerge in a way that challenges almost every assumption built into modern physics. As the energy grows dense enough in a confined space, the formation of miniature black holes becomes more than a hypothetical idea. It becomes a prediction derived from the structure of the equations themselves. The first thing to recognize about these tiny black holes is that they are not scaled-down versions of the enormous objects seen in the centers of galaxies. Large black holes, formed from collapsing stars or merging neutron stars, exist in environments where space-time curvature is intense, but not dominated by quantum fluctuations. Their horizons remain well-defined. Their masses stay stable unless they accrete material or emit Hawking radiation. The geometry around them follows predictable patterns. In contrast, miniature black holes are predicted to form at energy densities where quantum mechanics cannot be ignored. Their horizons, if they exist at all, fluctuate sharply because the energy creating them is uncertain. They do not persist for long, and their properties may not resemble those of larger black holes except in the most abstract sense. To see how such an object might arise, it helps to examine how gravity responds to energy concentration. According to general relativity, energy acts as a source of curvature. If a large amount of energy is packed into a small region, the curvature can grow severe enough that a horizon forms, a boundary beyond which signals cannot escape. For black holes of ordinary size, the mass involved is enormous. But the radius associated with a black hole scales with the mass. A black hole with the mass of a mountain would have a radius smaller than an atomic nucleus. A black hole with the mass of a proton would need to fit inside a region far smaller than anything encountered in particle physics. This is where the Planck scale becomes relevant. If the energy contained within a region reaches the Planck energy, the gravitational response becomes strong enough to cause collapse into a region that could behave like a black hole, even if the total energy involved is tiny. This collapse occurs not because of the mass alone, but because of the energy density. The energy required is enormous compared with anything achievable by human technology, but small compared with astrophysical scales. If you compress enough energy into a region of size comparable to the Planck length, even if the total energy is minuscule, gravity becomes overwhelmingly strong. The horizon that forms would be around the Planck length itself. Such a horizon would not resemble the smooth surfaces described in general relativity. Instead, it would be influenced by quantum fluctuations so large that the concept of a stable boundary becomes difficult to define. These miniature black holes would evaporate quickly through a process similar to Hawking radiation, but their evaporation would be extremely rapid, happening in a time interval comparable to the Planck time. The energy released in this evaporation would also be enormous compared to their size, but only within the confines of these extreme scales. The entire lifetime of such an object might be shorter than any meaningful interval in which classical physics could describe its behavior. As soon as it forms, it would begin evaporating, and the geometry around it would shift rapidly during the process. The region would be governed by a feedback loop. Quantum fluctuations influence curvature. Curvature influences the evaporation process, and the evaporation influences the fluctuations. This picture raises many questions. For one, it challenges the assumption that horizons must remain stable. In classical general relativity, horizons are smooth, continuous surfaces. They do not flicker or oscillate. But when quantum fluctuations become large, the energy density near the horizon shifts unpredictably. These shifts alter the curvature, causing the horizon to fluctuate as well. The horizon might expand, contract, or change shape on extremely short timescales. The idea of a single, sharp boundary may no longer apply. Instead, the horizon could behave more like a region of uncertain extent, defined only statistically over very short intervals. Another challenge concerns the interior of the miniature black hole. In larger black holes, the interior is described by a classical solution that includes a singularity. But for tiny black holes, the singularity predicted by general relativity cannot be taken seriously. The curvature near the centre would reach such extreme values that quantum mechanics must dominate the behaviour. The singularity is therefore replaced by something unknown, something requiring a unified description of quantum mechanics and gravity. It might be that the interior does not exist in any classical sense. Instead, the region could represent a temporary configuration in which space-time itself loses its familiar structure. A further complication arises from the question of information. Larger black holes give rise to the information paradox because the radiation they emit appears thermal, suggesting that information about the matter that fell in might be lost. For miniature black holes, the problem becomes even more intense. The rapid evaporation means that any information associated with the black hole must either remain inside a region that ceases to exist almost instantly, or be released in a highly chaotic burst of radiation. The standard tools of quantum mechanics are not equipped to handle this scenario because they require stable time evolution. The rapid fluctuations in space-time near the evaporating miniature black hole violate the assumptions that support unitary evolution. Whether information can survive this process is a question deeply tied to the structure of quantum gravity itself. The creation of miniature black holes also challenges the definition of a particle. In particle physics, particles are excitations of fields. But if the energy of a particle is high enough to create curvature comparable to that of a black hole, then the particle and the black hole begin to resemble different descriptions of the same configuration. Instead of a particle interacting with space-time, the particle becomes a region of space-time curvature. This raises questions about whether the distinction between particles and black holes is meaningful at extremely high energies. It might be that massive particles at sufficiently high energies must be treated as black holes. This would blur the boundary between matter and geometry even more. Another topic that arises in this context is the idea of a minimum length. General relativity allows space-time to be divided indefinitely, but quantum mechanics implies that measurement requires energy. The more precisely one tries to measure position, the more energy must be used. At the Planck scale, adding more energy to improve precision creates a miniature black hole preventing the measurement. This process establishes a natural minimum length, regardless of the details of any future theory. This minimum length acts as a limit on how small structures can be. Beyond that, no tool can probe further without collapsing the region into a black hole. Exploring these ideas leads to questions about the early universe. When the universe was extremely young, the density of energy was enormous, perhaps near the Planck density. In such an environment, miniature black holes could have formed frequently. They would have appeared and evaporated rapidly in a sea of intense radiation and quantum fluctuations. These events might have played a significant role in shaping the distribution of matter, the evolution of space-time, and the conditions that eventually led to a smoother universe. Even though these black holes would not survive to the present, their effects could have influenced large-scale structures indirectly. Some theories even suggest that these miniature black holes, if they formed in the early universe, might have left behind relics. These relics would represent stable configurations that no longer evaporate once they reach a certain size. If such relics exist, they could act as a form of dark matter. This possibility is speculative and would require new physics to stabilize the remnants, but it shows how miniature black holes may influence cosmology in unexpected ways. Other theoretical frameworks propose that black holes of different sizes could behave differently in higher dimensional environments. In theories with extra dimensions, the Planck scale might be lower than expected, allowing miniature black holes to form at energies accessible to particle accelerators. While experiments have not observed such phenomena, the idea illustrates how sensitive miniature black holes are to the structure of space-time itself. If the geometry includes dimensions beyond the familiar 3 of space and 1 of time, the threshold for black hole formation changes. The dynamics of these black holes could then reveal properties of those hidden dimensions. Even within familiar 4-dimensional space-time, miniature black holes challenge the meaning of curvature and energy. General relativity assumes that curvature describes the bending of space-time caused by energy and momentum. But near the Planck scale, the fluctuations in energy become so large that curvature may not be a useful quantity. Instead of a smooth bend, the geometry might oscillate rapidly between different configurations. In such an environment, the idea of curvature loses clarity. A miniature black hole formed in this setting would not be a simple geometric object, but a dynamic region shaped by the interplay between energy fluctuations and space-time instability. The questions surrounding miniature black holes extend into fundamental physics. If a unified theory of quantum gravity exists, it must describe these objects consistently. It must account for their formation, evaporation, and interactions with surrounding fields. It must handle the fluctuating geometry and maintain consistency with the principles of quantum mechanics. It must avoid singularities or provide a new interpretation of them. It must reconcile how information is stored and released, and it must do all these things while preserving the behavior of ordinary particles in large-scale space-time. Miniature black holes therefore represent not just an interesting prediction, but a benchmark for any proposed theory of reality. Their appearance is also deeply tied to the behavior of energy in extreme environments. As energy continues rising, the possibility of black hole formation becomes less a rare phenomenon and more an expected consequence. Understanding these conditions helps illuminate how the distinctions between particles, forces, and geometry collapse into one another when the environment becomes extreme enough. Far from being isolated oddities, miniature black holes contribute insight into the deeper structure behind all physical laws. The focus shifts from what might happen at extreme energies to whether those conditions can ever be produced by any method we could build or imagine. Many areas of science depend on experimentation, on the idea that a question can be probed directly if the right instrument is constructed. But as we approach the Planck energy, that expectation fades. It isn't simply that current technology falls short, or that building something more powerful would be expensive. The very structure of physics places a barrier that no machine, no collision, no design, no matter how advanced, could ever cross. The reasons for this barrier are rooted in the same principles that define the Planck scale itself. To begin, consider how particle accelerators operate. They propel particles to high energies and then collide them, turning kinetic energy into new particles, new states of matter, and new interactions that do not occur under ordinary conditions. Each generation of accelerators has revealed smaller structures and finer details of the universe. When the energy doubles, new thresholds open. When the energy increases tenfold, the resolution improves dramatically. It might seem reasonable to assume that by continuing this pattern, one could reach arbitrarily high energies. After all, nothing in principle prevents an accelerator from being larger, more powerful, or more sophisticated. But a closer examination shows that several fundamental constraints arise long before energies near the Planck scale. Some of these constraints come from engineering limitations, such as material strength, power requirements, and cooling needs. Others come from the behavior of charged particles in magnetic fields. However, even if one imagines overcoming all engineering challenges, using materials not yet invented, power sources beyond current capabilities, or sizes unthinkably large, certain constraints remain that cannot be avoided. These constraints appear because any attempt to reach Planck scale energies contradicts the rules that govern how matter and spacetime behave. One of the most immediate challenges is energy density. A particle accelerated to extremely high energy is not problematic by itself, but to achieve Planck scale energy, that energy must be confined to a particle or a region small enough to interact meaningfully at those scales. The moment energy is confined that tightly, gravity responds. The energy density becomes large enough that the region collapses into a tiny black hole, as described earlier. The accelerator never achieves a collision at the desired scale, because the energy concentration generates curvature so intense that it traps the energy inside a horizon. The machine destroys the conditions it is trying to create. This is not an engineering failure, but a consequence of the fundamental link between energy and curvature. Another difficulty comes from the scaling of accelerators. To increase the energy of charged particles, magnets must be used to bend their paths. Achieving higher energies requires either stronger magnets or larger circular paths. Magnet strength has physical limits tied to the materials used, and even hypothetical materials with perfect properties cannot provide infinite field strengths. Increasing the size of the accelerator offers more leeway, but the required radius becomes astronomical long before approaching Planck energies. Even a device the size of Earth's orbit would not suffice. A circular accelerator large enough to reach the Planck energy directly would require a structure so massive that its own gravitational field would collapse it long before completion. Linear accelerators face similar obstacles. They accelerate particles along a straight path using electric fields, but higher energies require longer paths. To reach Planck energy, the accelerator would need to stretch across distances far exceeding the size of the observable universe. Even if one imagines compressing field gradients to their theoretical maximum, these limitations persist. Space-time curvature, vacuum breakdown, and quantum effects disrupt the fields long before the necessary energies can be reached. It may seem tempting to consider focusing enormous energies into a small target instead of accelerating individual particles. Perhaps a sufficiently energetic laser, gravitational wave generator, or exotic device could achieve the same effect. But these methods also face barriers. Concentrating energy into a small enough region inevitably triggers gravitational collapse. The threshold is tied to the Planck energy and the Planck length. Anything attempting to compress energy beyond this limit simply produces a miniature black hole, instead of a controlled environment for studying quantum gravity. The act of focusing becomes self-defeating. Another issue arises from the availability of energy itself. The Planck energy is about 1019 times higher than the energy of particles produced in the most powerful human-made accelerators. To accelerate even a single particle to that energy would require more electricity than global civilization produces over long periods. But the scale becomes even more extreme when considering collisions. Collider experiments rely on smashing two beams together so the energy is shared between interacting particles. To probe Planck scale physics, one needs not just one particle at the Planck energy but two or more. the total energy requirement becomes absurdly large, far beyond any conceivable supply. Some might wonder whether natural astrophysical processes could do better. After all, cosmic rays reach energies higher than anything produced on Earth. The highest energy cosmic rays ever detected exceed the capabilities of any accelerator by many orders of magnitude. Yet even these cosmic rays fall dramatically short of the Planck energy. They reach energies around 1020 electron volts, which is still millions of times smaller than the Planck energy. These cosmic rays are produced by the most powerful environments in the universe, such as active galactic nuclei or gamma-ray bursts, yet none come close to Planck-scale energies. There are limits on natural processes as well. Magnetic fields in astrophysical objects have upper bounds. Shock acceleration mechanisms face constraints in efficiency. Particles accelerated in space interact with background radiation, losing energy before reaching the Planck scale. Even hypothetical events like collisions of cosmic strings or interactions in the early universe would have difficulty producing particles at Planck scale energies without immediately collapsing into black holes. One might attempt to circumvent these issues by considering environments where space-time itself provides the energy, such as regions near black holes or conditions in the early universe. Near a black hole's horizon, particles falling inward can reach incredibly high energies relative to one another. But reaching Planck energy requires conditions so extreme that the uncertainties in geometry and time make the concept of collision energy ambiguous. Moreover, any attempt to observe such collisions would require information to escape the region, which is prevented by the horizon. Another difficulty relates to measurement. Even if one imagines achieving Planck-scale collisions, how would the result be observed? Any detector must capture information about the event, but the event would be dominated by quantum fluctuations of space-time. The geometry would shift unpredictably. Signals would be distorted or trapped. The detector itself would be influenced by the same extreme curvature. A measurement device cannot survive an environment where space-time loses its stability. There is no meaningful way to record a signal from such an interaction. The information cannot be extracted without changing the outcome, and the act of measurement would collapse any localized geometry into a black hole before the measurement is complete. Some speculative ideas suggest that black holes could serve as natural probes of Planck-scale physics. If one studies Hawking radiation, or the behavior of horizons, one might infer properties of quantum gravity indirectly. But even these approaches do not provide direct access to Planck-scale interactions. The radiation emitted by a macroscopic black hole occurs far below the Planck energy. The geometry at the horizon is intense, but not extreme enough to reveal quantum gravitational behavior explicitly. Only black holes near the Planck mass would produce observable Planck-scale effects, but these objects evaporate too quickly to measure. Their properties cannot be observed without encountering the same limitations that prevent direct experiments. It is sometimes suggested that technology far beyond what humans currently possess, perhaps the technology of a hypothetical advanced civilization, might find ways around these barriers. But these barriers do not come from technology. They come from physics itself. No amount of engineering can violate the link between energy density and curvature. No manipulation of magnetic or electric fields can avoid the collapse threshold. No arrangement of lasers, mirrors, or gravitational devices can compress energy without invoking gravitational instability. The geometry of space-time responds to energy according to principles that cannot be bypassed. Even if one imagines using entirely new approaches, such as manipulating vacuum structure, engineering negative energy densities, or exploiting quantum entanglement, the limitations resurface. Negative energy, for example, appears in certain theoretical contexts, but the amount available is vanishingly small and constrained by quantum inequalities. It cannot stabilize regions of extreme curvature. Entanglement cannot move energy. Vacuum engineering cannot increase the density of energy beyond the point where gravity takes over. Every path ultimately intersects with the same boundary. The Planck scale is where our current physical descriptions break down, and no experiment can cross it without collapsing into a form that prevents meaningful observation. This does not mean, however, that Planck scale physics is forever inaccessible. It means only that direct experimentation cannot reach it. Science has often learned about inaccessible regimes through indirect means. We cannot travel inside stars, yet stellar physics is well understood through theory and observation. We cannot touch an atomic nucleus, yet nuclear physics is mapped with precision. In the same way, Planck-scale phenomena might be inferred through cosmological patterns, gravitational waves, or subtle signatures in particle interactions that occur at much lower energies. The boundary prevents direct observation, but not indirect understanding. The inability to reach the Planck frontier experimentally also shapes the development of theory. It encourages approaches that rely on mathematical consistency, symmetry considerations, or connections to phenomena that can be observed. Theories that unify quantum mechanics and gravity must produce predictions that align with known physics at accessible scales. They must reduce to quantum field theory and general relativity in the domains where those theories excel. They must avoid contradictions at the Planck scale, and even though no direct experiment can test them under Planck conditions, they must produce consequences that can be evaluated through astrophysics, cosmology, or lower energy experiments. When thinking about the early universe, it is tempting to imagine a single moment when everything suddenly appeared, already expanding, already glowing with energy, already following the laws we know today. Yet the physics of those first instants suggests something far stranger. The earliest moments did not resemble a familiar environment compressed to a smaller size. They belonged to a regime where the rules we rely on had not yet separated into their familiar forms. Temperatures and densities were so high that the usual distinctions between matter, energy, space, and time had not settled into the roles we assign them today. Although we cannot access those conditions directly, traces of them remain embedded in the universe's structure, offering hints about processes far beyond the reach of any experiment. To appreciate these clues, one must begin by recognizing how dramatically the universe has changed since those early moments. Today, space expands at a rate that can be measured. Galaxies form structures across billions of light years. Temperatures are low enough that atoms, planets, and stars can exist. Even the cosmic microwave background, the faint radiation left over from the early universe, has cooled to just a few degrees above absolute zero. Yet if we wind the clock backward, everything grows hotter and denser. Eventually the temperature becomes so high that atoms cannot form. Earlier still, nuclei cannot form. Earlier than that, even quarks and gluons behave differently, losing their confined structure. Each step we take backward leads to environments where matter behaves in unfamiliar ways. But none of these transitions compare to what happens near the Planck era. If we push far enough back before the earlier structures, before the formation of any particles we can name, before the emergence of the cosmic microwave background, we approach conditions where energies reach the Planck scale. The universe was astonishingly small, astonishingly hot, and astonishingly dense. Yet even this description uses language adapted to today's physical laws that may not have applied in that early phase. The idea of temperature, for example, depends on particles exchanging energy in predictable ways. At the Planck scale, where geometry fluctuates rapidly and matter loses its usual identity, the concept of temperature may not hold its usual meaning. Despite this uncertainty, the early universe still influences the universe we observe now. The challenge lies in determining which features of today's universe provide reliable clues about that era. We cannot observe the Planck era directly. Light could not travel freely. Space and time themselves shifted too quickly for signals to propagate in meaningful ways. And yet, the universe that exists now carries imprints of the processes that shaped it. These imprints appear in the distribution of galaxies, the small variations in the cosmic microwave background, the behavior of gravitational waves, and even in the ratios of certain particles and fields that persist across cosmic time. A key clue lies in the uniformity of the cosmic microwave background. This radiation fills the universe almost perfectly evenly, with tiny fluctuations that vary only at a level of 1 part in 100,000. Such uniformity suggests that regions now separated by billions of light-years were once extremely close together. But the puzzle becomes more complicated. According to classical physics, those regions should not have been able to exchange information or equilibrate because they were never in causal contact, yet they show nearly identical temperatures. This indicates that some process in the early universe must have allowed distant regions to share conditions before expanding apart. One interpretation is that the universe underwent a rapid expansion phase known as inflation. Inflation would smooth out irregularities and spread them across vast regions. But the idea of inflation itself raises questions. What caused it? What field or mechanism drove it? And what happened just before it began? Inflation suggests that the earliest universe may have existed in a state influenced by quantum fluctuations magnified to cosmic scales. These fluctuations, originating at sizes far smaller than atoms, were stretched across regions that later formed galaxies and clusters. Their patterns remain imprinted in the cosmic microwave background. That means the fluctuations we observe today may reflect the behavior of physics near the Planck scale, albeit indirectly. They represent the oldest signals accessible to observation. Another clue comes from the spectrum of these fluctuations. If one examines the slight variations in temperature and polarization in the cosmic microwave background, the fluctuations follow a pattern that suggests they originated from quantum processes occurring in a rapidly expanding environment. The fact that they align with predictions made by quantum field theory in curved spacetime is remarkable. It means that the universe remembers the quantum behavior of fields long before stable particles or forces emerged. Although we cannot see the earliest moments, we can infer that their fluctuations influenced later structures. These fluctuations also tell us something about gravity. The pattern of variations suggests that gravity behaved differently at early times, not in a way that contradicts general relativity, but in a way that hints at deeper structure. The fluctuations include effects that relate to both the curvature of spacetime and the quantum behavior of fields interacting with that curvature. Their properties suggest that gravity was sensitive to quantum effects, even though we lack a full theory describing these interactions. In this sense, the early universe functions as a natural laboratory for quantum gravity, providing evidence about how spacetime behaves when quantum fluctuations cannot be ignored. Another set of clues emerges from the ratios of different kinds of matter in the universe. The abundance of hydrogen, helium, and lithium produced during the first few minutes after the Big Bang depends on the conditions present when nuclear reactions first became possible. These abundances match predictions made by well-tested theories of nuclear physics, but the initial conditions used in those predictions trace back to the earlier stages of the universe. If the universe had expanded at a different rate or possessed different levels of curvature, the resulting element ratios would differ. The fact that the predictions match observations suggests that the early universe followed specific trajectories defined by deeper laws, even before those laws expressed themselves in familiar forms. One more area revealing hidden clues comes from the structure of cosmic expansion itself. The rate at which the universe expands today depends on the distribution of matter and energy, but it also carries traces of how expansion unfolded at earlier times. Certain features of the expansion history depend on processes that occurred while the universe was still dense and hot. The smoothness of the large-scale structure, the timing of different cosmic transitions, and the present-day distribution of matter all reflect the conditions set in the earliest moments. Although these clues do not reveal the Planck era directly, they create constraints on any theory that attempts to describe it. Whatever happened in those earliest periods must lead smoothly into the physics that we observe today. There is also the possibility that gravitational waves hold clues about the early universe. Long-wavelength gravitational waves, if produced during inflation or in earlier phases, could still exist today. They would stretch and compress space on scales far larger than galaxies, producing subtle signatures in the cosmic microwave background or in the timing of pulsars. These waves would carry direct information about how space-time behaved during the earliest instants. While such signals have not yet been observed definitively, ongoing experiments seek them. If detected, they would provide one of the clearest windows into conditions close to the Planck scale. Some theories propose even more dramatic clues. If the universe underwent transitions between different states defined not by matter but by the structure of space-time itself, these transitions might leave defects or remnants. These could take the form of cosmic strings, domain walls, or textures. Although none have been observed so far, their absence provides information as well. It suggests that if such transitions occurred, they must have done so smoothly, or at energies too high for remnants to persist. This again places constraints on what the earliest phase of the universe could have been. Another important clue involves the concept of entropy. The early universe had extremely low entropy compared to what the laws of statistical mechanics might predict. This low entropy state allowed the universe to evolve into its current structure. The origin of this low entropy remains a puzzle. One possibility is that the structure of space-time itself, at very early times, constrained the possible configurations of the universe. If space-time emerged from deeper quantum processes, those processes may have selected states with particular properties. The low entropy may therefore reflect the way those deeper processes function, offering yet another hint about the Planck scale environment. One could also look at the existence of dark matter as a potential clue. Dark matter does not interact with light but exerts gravitational influence. If it consists of particles, their properties may trace back to processes that occurred very early, perhaps after inflation or during reheating. The symmetry patterns that produce hypothetical dark matter candidates, such as axions or weakly interacting massive particles, may originate from physics that becomes relevant only near the Planck scale. If dark matter turns out to have properties tied to symmetry breaking at extreme energies, it would provide indirect evidence about the structure of the early universe. Dark energy, meanwhile, offers a different kind of clue. It governs the acceleration of cosmic expansion today. Its value appears extremely small compared with what quantum field theory predicts. This discrepancy may indicate something about the vacuum state of the early universe. Whatever processes occurred near the Planck scale may have shaped the vacuum configuration in a way that suppressed its gravitational influence. Understanding why the vacuum behaves as it does could reveal principles connected to the earliest moments. Even the dimensionality of the universe might reflect early conditions. Some theories propose that space-time started with different numbers of dimensions, only later stabilizing into the four-dimensional structure we observe. If true, the transition between different dimensional states might leave observable effects. These effects could manifest in patterns of cosmic expansion, in the behavior of gravitational waves, or in the relationship between quantum fields and curvature. If such patterns exist, they would provide insights into processes that occurred before the universe acquired its familiar form. What makes the early universe so informative is that it lived through energies no laboratory will ever reach. The conditions near the Planck scale were not artificially created, they were natural consequences of the universe's evolution. Even though that era lasted for an unimaginably short time, it shaped everything that followed. If we study the universe carefully enough, we may uncover the rules that governed those conditions long before they settled into the stable forms we study today. Since direct observation is impossible, theoretical models must rely on consistency, inference, and prediction. A viable model must generate the fluctuations we see in the cosmic microwave background. It must match the observed expansion history. It must align with the distribution of matter, the ratios of elements, and the existence of large-scale cosmic structure. Any theory that disagrees with these clues cannot describe the Planck era. This provides a set of tests, even if they are indirect. The universe itself becomes the experiment, and the analysis unfolds across billions of years. Trying to account for what happens when quantum rules and gravity operate together often feels like attempting to assemble a mechanism while lacking pieces that should exist, but have not yet been discovered. Every consistent theory in physics works beautifully in its own territory. Quantum mechanics excels at small scales, relativity governs the large, and quantum field theory handles the forces that shape matter. But no matter how far these frameworks are extended, none of them manage to describe what happens when energy becomes so intense that space-time itself fluctuates in quantum ways. Because of this, multiple ideas have been proposed to bridge the divide, each built on different assumptions, different mathematical structures, and different interpretations of what it means for the universe to be fundamental. These theories do not simply extend existing ideas, they reshape the foundations entirely, attempting to replace the incompatible pieces of our current frameworks with structures that remain consistent even at the Planck scale. One starting point for many proposals comes from recognizing that the smooth geometry of general relativity cannot survive under quantum conditions. If spacetime becomes wildly unstable at extremely small scales, then something must replace the continuous fabric described by relativity. Some theories suggest that spacetime is emergent rather than fundamental, that its structure arises from deeper processes that do not resemble geometry at all. Under this view, the geometry we see is a large-scale approximation, similar to how the smooth surface of a lake hides the molecules beneath it. At small enough scales, spacetime would not look like a fabric or a manifold, but something that behaves according to entirely different rules. One of the earliest and most influential attempts to reconcile gravity with quantum mechanics takes the form of string theory. Instead of treating particles as point-like objects, it treats them as tiny, vibrating strings. The different vibrational modes correspond to different particles. A single framework could therefore, in principle, describe all particles and forces. This shift from points to strings has a profound consequence. It softens the infinities that appear when trying to quantize gravity using point particles. A string has length, so interactions occur over finite regions rather than mathematical points, eliminating certain divergences. Moreover, one of the vibrational modes of the string corresponds to a particle, with properties matching those expected of the graviton, a hypothetical quantum particle that mediates gravity. This suggests that gravity emerges naturally from the theory, rather than being bolted on afterward. However, string theory introduces requirements that seem unfamiliar or even unsettling. The mathematics works only if the universe contains extra spatial dimensions beyond the ones we see. These dimensions must be compactified, rolled up or shaped in intricate ways so that they remain hidden at low energies. The energy scale at which these dimensions become relevant is close to the Planck scale. Many properties of particles, including their masses and interactions, depend on the shape of the extra dimensions. Small changes in the underlying geometry of these hidden dimensions could produce entirely different physical universes. This flexibility is both a feature and a problem. It allows string theory to describe many possible worlds, but makes it difficult to determine which description matches ours and why. Another approach that attempts to unify gravity with quantum mechanics is loop quantum gravity. Rather than adding extra dimensions or building particles from strings, it focuses on quantizing spacetime itself. In this view, spacetime is composed of discrete units, finite loops that combine to form a network. Geometry emerges from these networks. Distances, areas, and volumes are not continuous but quantized, meaning they come in discrete amounts. This quantization avoids the singularities predicted by general relativity, because curvature cannot become infinite if spacetime is built from discrete pieces. At extremely small scales, the loops change configuration in ways that produce the foam-like behavior expected from quantum fluctuations. As the scale increases, the network smooths out into the continuous geometry described by relativity. Loop quantum gravity has strengths that complement the weaknesses of string theory. It does not require extra dimensions, and it provides concrete predictions about how spacetime behaves near black hole horizons and in early universe conditions. Yet it also faces limitations. It currently does not incorporate the full range of particle interactions known from quantum field theory. Unifying matter with the quantized structure of spacetime remains an ongoing challenge. The theory explains how spacetime might behave at small scales, but does not yet describe the particles and forces that inhabit that spacetime with the completeness expected from a unifying theory. Another category of proposals explores the possibility that spacetime and gravity emerge from information. In these models, the geometry of the universe arises from the relationships between quantum states, particularly through entanglement. Entanglement describes how particles share information in ways independent of spatial separation. If entanglement patterns define the connectivity of quantum states, then spacetime itself could emerge from those patterns. Distances would reflect the degree of entanglement. Curvature would represent changes in entanglement structure. Gravity could arise from the tendency of entanglement to distribute itself in ways that follow thermodynamic or statistical principles. This information-based view has gained traction because several results in theoretical physics suggest deep connections between geometry and entropy. Black hole thermodynamics, for example, shows that a black hole's horizon area corresponds to its entropy. The holographic principle suggests that the amount of information within a region of space is proportional not to its volume, but to its surface area. These clues hint that space-time may be a large-scale expression of microscopic information storage. If true, then gravity is not a force in the usual sense, but a reflection of how information is arranged. The geometry we observe emerges from deeper patterns in the quantum state of the universe. Even with these promising insights, information-based approaches raise new questions. If space-time emerges from entanglement, what constitutes the underlying system that carries this entanglement? What principles govern its behavior? And how do familiar particles arise from these deeper structures? Some variations of the theory propose that particles correspond to patterns or defects within the underlying informational network. Others propose that gauge symmetries, those that govern electromagnetism and other forces, arise from properties of the entanglement configuration. Although these ideas offer appealing conceptual frameworks, they require extensive development to match the predictive power of existing theories. Another family of proposals focuses on causal structure. Instead of treating spacetime as a continuous fabric, these models treat it as a network of events linked by causal relationships. The order in which events can influence one another defines the structure of spacetime. If the network of causal links is fundamental, then geometry emerges from the large-scale behavior of those links. Distances come from the number of steps required to connect two events. Time emerges from the ordering of events. Gravity arises from the density of connections and the way the network grows or rearranges itself. Causal set theory takes this approach seriously. It proposes that spacetime consists of discrete events arranged according to a partial order. The network grows randomly according to specific rules that ensure Lorentz symmetry at large scales. The smooth geometry of relativity arises when the number of events becomes large enough. Quantum fluctuations in the early universe reflect randomness in how the network developed. The theory provides a clear way to represent spacetime as discrete, but remains incomplete in describing matter and interactions. Other proposals investigate how symmetries change at extreme energies. Some theories suggest that the symmetries governing particles and forces become enlarged or modified near the Planck scale. When energies are low, these symmetries break, producing the distinct particles and forces we observe. At high energies, the symmetries may unite, merging forces into a single structure. If gravity shares this deeper symmetry, then its behavior at small scales would be governed by rules that differ fundamentally from general relativity. These ideas appear in grand unified theories, supersymmetry, and various attempts to combine these structures with quantum gravity. Supersymmetry, for instance, proposes that each particle has a partner particle differing in spin. These partner particles stabilize certain quantum corrections and help unify the forces at high energies. If supersymmetry were exact, it could offer a path toward unifying gravity with quantum mechanics by organizing particles and forces into a more symmetric framework. But supersymmetry must be broken at low energies, or we would observe partner particles in current experiments. Efforts to detect supersymmetric particles have not yet succeeded, raising questions about where the theory might fit. Some unifying theories propose that the number of dimensions is not fixed. Instead, the dimensionality of the universe may depend on scale. At extremely high energies, space-time may behave as though it has fewer dimensions. As the energy decreases, the dimension count increases. This concept appears in several approaches, including asymptotic safety and certain forms of quantum geometry. If true, it would explain why gravity becomes weaker at larger scales and extraordinarily strong at the Planck scale. It also suggests that the structure of space-time itself is not constant across energy ranges. Asymptotic safety attempts to treat gravity as a quantum field theory that becomes well behaved at high energies. It posits that the theory reaches a fixed point where the parameters stop diverging. If the theory stabilizes in this way, then gravity can be quantized without needing strings or discrete structures. The theory would remain predictive across all scales. While promising in some formulations, the approach requires extremely complex calculations, and its full consequences remain under investigation. Other ideas focus on modifying quantum rules rather than space-time. These propositions argue that quantum mechanics itself must be adjusted to account for gravitational effects. They explore ways to embed uncertainty principles into curved space-time, or propose new commutation relations between position and momentum that incorporate minimal length scales. These modifications aim to bridge the gap between quantum theory and gravity by altering the foundational rules rather than the geometry. Still more speculative ideas propose entirely different starting points. Some treat the universe as a holographic system, where the true description exists on a boundary rather than in the interior. Others treat the universe as a computational structure, with physical laws emerging from the evolution of an underlying algorithm. Some imagine that space-time emerges from group symmetries or algebraic structures. In all these cases, geometry and matter arise from mathematical relationships more fundamental than space and time. Despite their variety, all these theories share a common goal: to produce a coherent picture of the universe that does not break down when energy reaches the Planck scale. Each theory provides partial insights, partial resolutions, and partial predictions. None of them fully account for everything we observe, yet each contributes ideas that help shape our understanding of what a complete theory must accomplish. Most attempts to understand nature rely on a familiar strategy. Whenever something looks complicated, break it into smaller parts. This approach works almost everywhere. Molecules break into atoms. Atoms break into electrons, protons, and neutrons. Protons and neutrons break into quarks. Forces break into individual carriers. Even fields can be decomposed mathematically into simpler components. The habit becomes so ingrained that we often assume it must continue indefinitely, that smaller pieces always exist beneath whatever scale we reach. But the Planck scale challenges this assumption directly. If there is a point beyond which the familiar notion of smaller loses meaning, then the entire logic supporting reduction, subdivision, and decomposition begins to unravel. At that point, our most trusted methods of analysis must be replaced with ideas that do not depend on smaller building blocks. To see why this question matters so deeply, one must first consider how much of physics depends on the ability to define parts. When describing the motion of a planet, the planet is treated as a body with definite properties. When describing the behavior of a gas, the gas is treated as a collection of molecules. Quantum mechanics describes particles as excitations of fields, but still relies on the concept of distinct states that can be resolved in principle. Even theories proposed to unify gravity and quantum mechanics begin by specifying the underlying ingredients, whether strings, loops, networks, or algebraic objects. The entire structure of science assumes that reality can be subdivided into meaningful components. However, once energies approach the Planck scale, the tools used to separate reality into parts begin losing reliability. If you try to isolate an extremely small region to measure its properties, the act of measurement injects energy so intense that curvature becomes enormous. The region collapses into a miniature black hole. This collapse halts further subdivision. It is not simply a practical obstacle, it is a signal that space-time itself refuses to support being divided beyond a certain limit. If length cannot be defined below the Planck length, then the very idea of smaller pieces becomes questionable. A limit on how fine reality can be divided implies that the foundations of physics must be built on different principles. The challenge becomes clearer when considering what smaller pieces actually mean. In classical physics, a smaller piece is a smaller region of space containing a smaller amount of matter or energy. But if space-time lacks stability at small scales, if regions fluctuate or dissolve into quantum foam, then dividing reality into smaller spatial regions becomes meaningless. Space cannot be subdivided in a way that produces well-defined outcomes. In quantum mechanics, one can subdivide the state space of a system arbitrarily, but that subdivision relies on the assumption that space and time remain well-defined parameters. If those parameters lose meaning, the structure of the state space must change as well. It also becomes difficult to define particles when the underlying geometry fluctuates. The identity of a particle depends on the stability of its associated field and the possibility of distinguishing that field's excitations from those of other fields. If geometry is constantly shifting, fields cannot maintain their structure. A particle might not exist as a localized excitation, but as a temporary pattern influenced by both quantum fluctuations and gravitational curvature. In such an environment, the concept of a particle breaks down. It cannot be treated as a building block when the boundaries defining it are unstable. This issue extends to forces as well. Forces rely on symmetries in physical laws, and those symmetries require space-time to behave consistently. If space-time cannot be defined at very small intervals, the symmetries governing the forces cannot be extended into those regions. A force is not simply a relationship between particles, it is a structure defined by how fields behave in space-time. If space-time lacks structure at certain scales, forces lose their definitions there as well. One of the more striking consequences of having no smaller pieces is that geometry itself may not be fundamental. Instead of treating space as something that can be subdivided, one must treat it as something that emerges from more primitive relationships. In that view, distances, angles, and dimensions arise only when large-scale patterns stabilize. Below that threshold, there are no geometric parts to divide. The Planck scale represents the point where geometry begins, not where it ends. Smaller pieces do not exist because geometry itself does not exist below that limit. This perspective leads to another consideration. If reality has no smaller pieces, then the universe must be described using concepts that do not rely on parts. Instead of asking what something is made of, one might ask what structures describe how it behaves at different scales. Instead of breaking a system into components, one might analyze how the relationships among its elements produce observable patterns. This shift mirrors trends already seen in certain theoretical approaches, where networks, symmetries, or information structures replace particles and fields as the primary objects of study. It is also possible that the emergence of space-time depends on collective phenomena. In condensed matter physics, the properties of materials often arise from interactions between large numbers of particles. A crystal has a structure that does not exist when only a few atoms are considered. Superconductivity emerges from cooperative behavior at low temperatures. These phenomena reveal that new laws can emerge when many identical units interact. If space-time emerges in a similar way, then its smaller scale would not be built from smaller components, but would reflect the limits of a collective phenomenon. The Planck scale might represent the point where space-time stops behaving like an emergent structure and begins dissolving into more fundamental processes. Another consequence concerns the nature of dimensionality. Our universe appears to have 3 spatial dimensions, but some theories suggest that this number may change depending on scale. At large scales, the universe behaves as though it has 3 dimensions, but at extremely small scales, dimensionality may reduce. If the number of dimensions decreases as energy increases, then the concept of subdividing space becomes even more problematic. A lower dimensional environment cannot support the same kinds of subdivisions that ordinary 3-dimensional space allows. In such a scenario, smaller pieces do not exist because the very concept of volume loses meaning at small scales. These ideas may seem abstract, but they lead to concrete implications. For example, if reality has no smaller pieces, then physical properties such as mass or charge cannot be defined by something internal to particles. Instead, they must be properties of interactions or symmetries. A particle would not possess mass because it contains something massive. It would possess mass because it interacts with fields or geometry in a particular way. If geometry fails to exist below the Planck scale, then mass, charge, and spin might reflect modes of a deeper structure that does not involve subdivision. One might also consider whether the laws of physics themselves emerge from deeper principles. If reality has no smaller pieces, then the laws we know must arise from constraints that apply only at larger scales. These constraints could be statistical, combinatorial, or informational. They might emerge because the universe must obey certain consistency conditions to exist at all. In such a view, the laws governing particles and forces would be analogous to the laws governing large-scale behavior in statistical mechanics. They would not be fundamental but emergent. A related concept appears in theories proposing that spacetime emerges from entanglement. If entanglement creates effective geometry at large scales, then there is no geometric structure beneath those scales to subdivide. The fundamental components would be relationships between quantum states, not pieces of space. Reality would be relational rather than structural. Attempts to subdivide space would fail because space would not exist independently of those relationships. An environment with no smaller pieces would also challenge our understanding of measurement. Measurement relies on interactions between systems, but those interactions assume that space and time define the framework in which measurement occurs. If the framework disappears at small scales, measurement becomes undefined. One cannot determine the position of a particle if position itself loses meaning. One cannot measure time if time does not provide a stable background. The uncertainties of quantum mechanics would not simply increase, they would reflect the breakdown of the underlying concepts being measured. This raises an important question. What becomes of causality if there are no smaller pieces? Causality depends on the ability to distinguish between events and to track how one event influences another. But if space-time does not exist at small scales, then distinguishing between events becomes impossible. Causal structure may emerge only when space-time stabilizes. Below that threshold, there may be no temporal ordering. This does not mean that events occur randomly. Instead, the concept of an event may not apply. The universe may obey relationships that do not rely on cause and effect in the familiar sense. The absence of smaller pieces also has implications for energy. Energy is defined through the behavior of fields in spacetime. If spacetime is not fundamental, energy may be another emergent property. It may reflect the way patterns in the system evolve over time, not a quantity possessed by objects. The concepts of momentum, force, and action might belong only to the emergent regime where spacetime provides a consistent stage. In the regime without smaller pieces, these concepts could dissolve or take unfamiliar forms. One way to visualize this is to imagine a system where the smallest meaningful structures are not objects but transitions. Instead of viewing the universe as composed of parts, one might view it as composed of transformations, with states defined only through relationships among these transformations. In such a model, the Planck scale marks the boundary beyond which no objects exist, only processes. The processes do not occur in space. They create the appearance of space when many of them act together. Another possible implication is that time may not be fundamental. If time emerges only when spacetime stabilizes, then below the Planck scale, there may be no time at all. Processes might not unfold in sequence, but exist in configurations that give rise to time only when viewed at larger scales. The idea that there are smaller pieces of time would not make sense because time would not exist independently of the structures that create it. Recognizing that reality may have no smaller pieces forces a reconsideration of what it means for something to be fundamental. Instead of looking for the smallest entities, physicists may need to search for the most universal relationships, relations that remain consistent even when traditional structures dissolve. The ultimate theory of nature may describe patterns, constraints, or mathematical consistencies rather than objects. The conversation shifts from describing what the universe does to confronting what the universe allows us to know. For most of scientific history, progress followed a reassuring pattern. When something seemed mysterious, better instruments, sharper logic, or more disciplined mathematics eventually revealed the answer. Telescopes overcame distance, microscopes overcame scale, spectroscopy overcame invisibility, particle accelerators overcame energy limitations. Each frontier yielded to a combination of creativity and engineering. This steady expansion of knowledge produces an understandable expectation that all mysteries might eventually yield if enough time and effort are invested. Yet when approaching the Planck scale, that expectation meets a boundary unlike any humanity has faced before. The Planck barrier does not merely frustrate our current abilities, it challenges the assumption that knowledge can always be deepened by examining smaller structures or pushing to more extreme conditions. This shift becomes clearer when examining how science typically grows. One generation of inquiry pushes against the limits known at the time. The next develops tools that push beyond those limits. Light once seemed the fastest possible influence until relativity explained why that limit exists. Atomic structure once seemed indivisible until quantum mechanics revealed layers beneath it. Even black holes, once feared as mysteries, are now studied through observations and gravitational wave detections that would have seemed impossible decades ago. Across these examples, limits served not as barriers, but as guides to deeper understanding. With the Planck barrier, the situation changes because the barrier is encoded in the laws themselves. It does not represent a region we cannot reach today, but might reach later. It represents a region that the universe does not permit us to access by any method consistent with the laws that govern everything else. No matter how advanced our civilization becomes, no instrument can probe distances shorter than the Planck length without collapsing the attempt into a miniature black hole. No measurement can stabilize spacetime intervals shorter than the Planck time because spacetime itself fluctuates too violently. No particle can be accelerated to Planck energy without triggering gravitational collapse. These limits are not technological, they are structural. Understanding what this means requires stepping back from the physics and examining the logic beneath it. Scientific knowledge often relies on the ability to isolate systems. If a smaller part behaves differently from a larger whole, then studying the small part reveals how the larger system emerges. This approach works in chemistry, biology, condensed matter physics, and quantum field theory. But when the universe imposes a smallest meaningful scale, isolation becomes impossible below that point. The system cannot be subdivided. The phenomena that occur at or below the Planck scale do not produce stable signals that can be detected or measured. Any attempt to measure them changes the system so drastically that the measurement substitutes collapse for understanding. This does not mean those processes do not exist. It means that they cannot be accessed through the usual methods of inquiry. A mystery can exist, yet lie outside the range of what can be known through experiment. In most of physics, the unknown feels temporary, something that awaits new ideas or tools. The Planck barrier introduces the possibility that some aspects of reality are fundamentally inaccessible, not because they lack explanation, but because explanation requires information the universe will not allow to be gathered. The difficulty deepens when considering the role of spacetime in knowledge. Spacetime is not just a background where physics occurs, it is the medium through which information travels. Signals move through spacetime, experiments occur in spacetime, distances, durations, and causal relationships shape what can be learned. If spacetime itself ceases to exist in meaningful form below the Planck scale, then the very structure that supports knowledge dissolves. A measurement cannot occur if there is no stable time interval in which to compare events. A location cannot be identified if there is no stable geometry to define coordinates. Below the Planck scale, not only does physics lose meaning, but the requirements for knowledge themselves break down. Another issue arises when considering the meaning of explanation. An explanation in science typically describes how one phenomenon arises from another. A stone falls because gravity curves space-time. Atoms emit light because electrons transition between energy levels. Stars shine because nuclear fusion converts mass to energy. These explanations rely on the idea that cause and effect operate in a consistent framework. But at the Planck scale, the notion of cause and effect becomes unstable. If time loses its familiar structure, events cannot be ordered reliably. Without predictable ordering, explanation becomes difficult to define. One cannot explain how something arises from something else if the sequence connecting them cannot be stabilized. Some theoretical frameworks attempt to describe the region below the Planck scale, but even these theories confront the limits of knowledge. String theory, loop quantum gravity, causal set theory, and holographic models all propose structures more fundamental than space-time. Each provides a way to avoid the breakdowns predicted by general relativity and quantum mechanics. But none of these theories can be tested directly in the domain they attempt to describe. Their predictions must be inferred indirectly. They may offer mathematical consistency, philosophical appeal, or internal coherence, but they cannot currently be verified by examining the processes they claim to describe. This creates an unusual scenario in science. Traditionally, theories grow through two mechanisms. They predict outcomes that can be tested, or they explain known phenomena more effectively than previous theories. At the Planck barrier, prediction breaks down because the relevant conditions cannot be accessed experimentally. Explanation becomes indirect because the data that would reveal whether a theory is correct cannot be gathered. Instead, the only tests available concern whether a theory aligns with lower energy physics and whether it remains mathematically consistent when approaching the Planck scale. This forces a shift in scientific methodology, one that values internal coherence and deep symmetry more heavily than direct experimental confirmation. This situation has led some thinkers to suggest that the Planck barrier represents the ultimate limit of empirical science. But while that view acknowledges the constraints imposed by physics, it may be too pessimistic. There are still ways to learn about the Planck era, or at least to narrow the range of possible theories through indirect evidence. The earliest universe, black hole behavior, and cosmological structure all carry signatures of processes that occurred when energies were far higher than anything achievable now. These traces may not reveal every detail, but they can eliminate theories that contradict observations or fail to produce the right large-scale behavior. However, even indirect clues have limits. If the universe smoothed out fluctuations through processes like inflation, many details of the Planck era may have been erased. If black holes conceal their quantum gravitational behavior behind horizons, only subtle signatures of their internal processes can escape. If space-time emerges from deeper structures, many features of those structures may be hidden forever from observation. The universe does not promise that deeper knowledge is always available. It only promises that the knowledge we can obtain will remain consistent with the constraints under which the universe operates. This leads to a deeper philosophical question. If the Planck barrier prevents direct access to certain truths, does it imply that those truths are unknowable or simply inaccessible to our current form of inquiry? The answer may depend on what we consider knowing. If knowing requires measurement, then the barrier may indeed define an ultimate limit. But if knowing can include understanding principles that govern the inaccessible region, principles inferred from consistency, symmetry, and indirect effects, then the barrier may not be absolute. It may instead define the boundary between what can be observed and what must be reasoned from the edges. In this sense, the Planck barrier mirrors other limits that have shaped science. The speed of light is an absolute limit on how fast information can travel, but it does not prevent understanding. The uncertainty principle limits the precision with which quantities can be measured, but it does not prevent theoretical clarity. Absolute zero cannot be reached, yet understanding of quantum systems near that limit has flourished. The Planck barrier may fit into this tradition, a limit that shapes our relationship with knowledge rather than ending it outright. Yet the barrier remains distinctive because it challenges not only the limits of measurement, but the foundational concepts of physics. It suggests that some descriptions of the universe cannot be translated into familiar forms like particles, fields, or events. It implies that the universe may possess layers that do not resemble objects or processes. It reveals that the scaffolding supporting physical reasoning, space, time, causality, measurement, may itself be emergent. When facing a boundary like this, traditional scientific language becomes strained. Theories may rely more on mathematical abstraction than on physical analogy. Interpretations may require giving up long-standing intuitions about what reality is made of. This shift influences not only the theories, but the expectations placed upon them. A successful theory of quantum gravity must describe what happens when space-time dissolves, when particles lose identity, when forces merge, and when no smaller pieces exist. It must also remain consistent with all known physics at lower energies. But beyond this, it must accept that certain details may be fundamentally beyond reach. A complete theory may not answer every question. It may instead define which questions have answers and which do not. This perspective reshapes the meaning of progress. Progress no longer means peeling back layers indefinitely. Instead, it could mean understanding the limits of inquiry, identifying the principles that remain valid across all scales, and discovering frameworks that describe reality even when traditional concepts fail. It may mean accepting that some aspects of the universe are not hidden, but inherently undefined at certain scales. There comes a point in any attempt to understand the universe where the remaining questions feel less like missing pieces of a puzzle and more like signs that the puzzle might not have been designed for completion. The Planck scale, with its unyielding constraints and unreachable energies, illustrates this feeling more than any other domain in physics. It appears to mark the threshold where the universe refuses to reveal more. The rules we know, the particles we catalogue, the forces we measure, the symmetries we uncover, all of them arise from underlying principles that become inaccessible once conditions reach the deepest levels possible. To grasp why this secrecy exists, it helps to examine not just the physics involved, but also the structure of the universe as a system that both invites and restricts understanding. One of the first insights comes from recognizing how unusual it is for nature to impose absolute limits. Most limitations encountered in science eventually yield to new techniques. Before telescopes existed, the stars seemed unknowable. Before microscopes, cells were invisible. Before spectrometers, chemical composition could not be analysed. The history of science is filled with boundaries that seemed final until they weren't. Even quantum mechanics, with its uncertainty principles, does not forbid understanding. It only forbids certain kinds of precision. The universe almost always provides a different pathway when one approach becomes blocked. Yet the conditions around the Planck scale do not appear to leave alternative paths. They form a boundary embedded not in technology or method, but in the definition of the physical world itself. This raises a natural question. Why would nature establish a threshold that guarantees certain truths remain hidden? What purpose does such secrecy serve? The answer is not that the universe hides information deliberately, but that the foundations of the universe do not permit that kind of information to exist in stable form. The constraint is structural, not intentional. To see this more clearly, one can begin with how energy behaves when it becomes extremely concentrated. As energy grows within a confined region, gravity strengthens in proportion to the density. If the concentration becomes high enough, the region collapses into a black hole. This tendency occurs whether the energy comes from particles, radiation, or fields. Gravity's reaction ensures that any attempt to push deeper into subplanckian scales triggers a phenomenon that erases the very conditions being created. The collapse prevents access to smaller structures because smaller structures cannot remain stable. The universe does not hide deeper layers. It prevents those layers from forming in ways that can be inspected. Another essential point involves the way fluctuations behave at extreme scales. Quantum mechanics dictates that uncertainty grows when confinement increases. If you attempt to localize energy into a very small region, the uncertainty in its momentum becomes enormous. That uncertainty expands outward, making the system uncontrollable. Gravity then responds to that unpredictable distribution of energy, creating chaotic curvature that prevents stable measurement. The Planck boundary arises from this cooperation between uncertainty and curvature. One enforces unpredictability, the other enforces collapse. Together they form a self-reinforcing barrier that ensures no experiment, no matter how advanced, can yield clarity beyond the limit. This interplay hints at a deeper explanation. The universe remains consistent only because such a boundary exists. If there were no limit on how small a region could be examined, the framework of physics might collapse into contradictions. Many theories depend on the assumption that space and time behave consistently across scales. But below the Planck scale, the assumptions about geometry, continuity, and localization break down. If nature allowed such regions to exist in accessible form, the laws used to describe everything else might not hold together. By imposing a limit, the universe preserves the coherence of the larger scale laws. There is also the matter of stability. The universe's large-scale structure depends on the consistency of physical laws across enormous distances and times. Stars form, galaxies rotate, planets orbit, and atoms maintain their shapes because the laws never change unexpectedly. But if sub-Planckian behavior were observable, quantum fluctuations of space-time could ripple outward, influencing larger structures. The universe might lack the stability needed for complexity to arise. Secrecy at the Planck scale is therefore closely tied to the stability of everything above it. The hidden region acts as a foundation that supports the knowable universe by shielding it from the chaos beneath. This perspective aligns with the way many emergent systems behave. In various fields of science, complex phenomena appear only when deeper layers remain inaccessible or irrelevant. For instance, the solidity of a material emerges from molecular interactions, but the everyday world does not need to track the motion of individual electrons to function. Biological organisms rely on molecular processes, but their behavior is not governed by atomic details in a direct sense. Large-scale behavior depends on a coarse-grained structure where deeper layers do not interfere continuously. If one could inspect every microscopic fluctuation in real time, the emergent structure might lose coherence. In a similar way, the Planck layer may be inaccessible because its visibility would destroy the predictability that higher layers require. Another way to understand the secrecy is to consider how information is stored and transmitted. Information about physical systems typically travels through space-time. But if space-time itself breaks down into rapid fluctuations at small scales, then information cannot propagate reliably. No signal can survive the instability long enough to be meaningful. Even if someone could create a process at the Planck scale, no knowledge of that process could escape the region without being scrambled by geometric uncertainty. The secrecy, therefore, emerges naturally. Information cannot escape a domain where the medium for information is itself undefined. Some thinkers argue that the secrecy is not merely a limitation, but a consequence of how the observable universe emerges. If space-time arises from deeper relationships, whether entanglement, causal networks, or algebraic structures, then the Planck scale marks the transition where these relationships become too fine-grained to produce meaningful geometry. It is not that the universe prevents us from seeing deeper, it is that deeper has no meaning independent of the emergent structures that form above the Planck boundary. Below that boundary, the concepts required to define knowledge, distance, sequence, energy, location, do not exist in the usual sense. This interpretation suggests that the universe's deepest energies remain secret because they belong to a domain without the language required for description. The familiar categories of physics apply only after spacetime becomes smooth enough for geometry to emerge. Asking what lies below the Planck scale may be similar to asking what lies north of the North Pole. The question uses concepts that cease to apply once the boundary is crossed. Another insight comes from examining how singularities behave. In general relativity, singularities represent points where curvature diverges and the equations break down. But these points are usually hidden behind horizons. The universe protects incomplete mathematical descriptions by preventing direct observation of the regions where they break. The Planck barrier generalizes this pattern to all of physics. Wherever the equations produce contradictions or infinities, the universe restricts access. The secrecy is not an obstacle, but a safeguard. This pattern also appears in the behavior of black holes on quantum scales. If miniature black holes evaporate rapidly, reverting to radiation before any signals can escape, then the interior remains hidden forever. It is not that the interior contains forbidden information. It is that the laws of physics guarantee that the information inside cannot be transported outward in a stable form. The Planck barrier extends this principle across all of space-time, ensuring that the ground-level rules remain inaccessible because access itself would violate those same rules. Another perspective involves the consistency of physical laws. If deeper layers were accessible, different regions of the universe might evolve under different micro-laws. The Planck barrier ensures uniformity. It provides a single emergent structure capable of supporting the physics we observe everywhere. Without the barrier, the universe might not operate under universal laws at all. This uniformity is essential for understanding. Knowledge requires consistency. Where consistency cannot be preserved, knowledge cannot emerge. The barrier maintains the conditions needed for the existence of coherent understanding. Considering these points, one might conclude that secrecy at the Planck scale is a necessary feature rather than a flaw. It ensures that the universality of physics holds, that emergent structures remain stable, that energy cannot disrupt the geometry that supports complexity, and that measurement does not undermine the framework in which it occurs. The universe keeps its deepest energies secret, not by intention, but because those energies belong to a regime incompatible with observation, measurement, or interpretation. This perspective also clarifies why every attempt to describe the Planck domain mathematically produces multiple competing theories. Each theory attempts to reconstruct the rules that govern a region where the usual concepts break down. But because no data can confirm or reject these ideas directly, the gap between mathematics and observation remains wide. The secrecy manifests as theoretical openness. Many paths remain possible because none can be closed through experiment. Understanding why the universe maintains this secrecy may help guide how theories should be developed. Instead of expecting complete access to the deepest layers, researchers may focus on identifying principles that remain consistent across scales, constraints that any viable theory must satisfy, and signatures in the observable universe that reflect the influence of deeper structure without revealing it directly. The secrecy becomes a signpost. Theories must respect the boundary rather than attempt to cross it. Seeing the Planck barrier in this light also reframes the idea of scientific limit. Instead of representing a failure of human capability, it reveals something profound about the nature of reality. The universe provides stable laws, emergent structures, and predictable behavior at the scales where life, matter, and complexity exist. The cost of this stability is that the foundation cannot be exposed. The deepest energies remain hidden because exposing them would undermine everything built upon them.